Hello there, and welcome back to The Sleep Science, where you and I wander through the kind of mysteries that hide right under your nose, literally. Tonight, we're going to peel back the curtain on something you've been swimming through your entire life but rarely think about, the invisible ocean of chemistry that surrounds you. You breathe it, move through it, and depend on it, but you almost never see it. You probably won't survive this particular experiment. Don't worry, not because it's dangerous, but because technically no one ever survives a night without air. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you do, drop your location and your local time in the comments below. It's always oddly comforting to know how scattered across the globe this little sleepy science family really is. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You sit back, breathing in what feels like nothing. The room seems still, quiet, neutral. But of course, nothing could be further from the truth. Each breath you take is a wild festival of molecules. Nitrogen, oxygen, argon, carbon dioxide is swirling together like invisible confetti in a constant chaotic ballet. You can't see them, but at this very moment, around 26 sextillion molecules are bumping into your skin every second. You're bathed in motion, an invisible tide of chemistry pressing gently against you from every direction. When you inhale, you're drawing in roughly 78% nitrogen, 21% oxygen, a whisper of argon, and a trace of carbon dioxide. But the air's personality doesn't end there. Lurking among those ordinary gases are tiny guests, water vapor molecules drifting lazily, dust motes too small to see, spores and bits of pollen, the occasional rogue molecule of methane or ozone. If you could suddenly see it all, the world would shimmer like a dense fog of motion. You'd probably start sneezing from sheer disbelief. You take another breath and imagine following it inward. The oxygen molecules, those tiny double-bonded O2 entities, dive into your lungs, meeting red blood cells like VIPs at a microscopic nightclub. Hemoglobin, the bouncer/chaperone of the bloodstream, grabs oxygen tightly, holds it for a while, then releases it exactly where it's needed. It's chemistry as choreography, everything timed, precise, invisible. A century ago, scientists were still arguing about what made air vital. Was it something mystical, or was it mechanical? Historians still argue whether the discovery of oxygen by Priestley and Lavoisier was more accident or enlightenment, but either way, it shattered the illusion that air was empty. It revealed the air itself to be alive with reaction. If you have ever stood on a windy hill and felt the gust against your face, you felt pressure, the accumulated push of countless molecules colliding in synchronized chaos. When the wind howls, that's not air moving in some solid wave, it's zillions of invisible atoms elbowing one another forward like commuters in a rush-hour train station. The average molecule in that wind travels at about 1,000 miles per hour. That's right. While you sit here yawning, the air is in constant or high-speed turbulence all around you. Yet somehow, all that speed feels like stillness. That's one of nature's better jokes. The chemistry of air has been shaping life since the very beginning. Billions of years ago, Earth's atmosphere was a toxic brew. Methane, ammonia, carbon dioxide, and barely a whiff of oxygen. The first bacteria that learned to harness sunlight changed everything, releasing oxygen as waste. Waste, the byproduct of ancient photosynthesis, turned out to be the gas you can't live without. Somewhere out there, a cyanobacterium is still laughing at you. And while oxygen gets the spotlight, nitrogen quietly dominates the show. It doesn't react easily. It's too stable, a stubborn pair of atoms locked together by a triple bond that refuses to break without serious coaxing. But that's exactly what makes it the perfect background player. Nitrogen fills your lungs without setting anything on fire. Yet certain bacteria and lightning bolts can crack it open, turning it into ammonia, nitrates, and other compounds that plants depend on. Every time you eat a salad, you're basically chewing lightning and microbe magic. The air also carries secrets of history. In the 1600s, chemists believed in phlogiston, a mysterious fire element that escaped during burning. It wasn't until the late 18th century that Antoine Lavoisier, working with meticulously sealed glass containers, proved that burning was a union with oxygen, not the release of some invisible fire spirit. His experiments birthed modern chemistry, but also ended with him being guillotined during the French Revolution. You might say that was one reaction he didn't predict. Even now, the chemistry of air keeps rewriting itself. In cities, car exhaust adds nitrogen oxides that later morph into ozone, a molecule you want high in the sky but not near your lungs. In forests, terpenes from pine needles mix with oxygen to form delicate aerosols that scatter sunlight and make the air smell green. Those invisible molecules can actually influence cloud formation. When you smell a forest after rain, you're inhaling a whole ecosystem of reactive chemistry. You're not just breathing air, you're breathing stories of soil, tree, and sky, all compressed into invisible form. Take a slow breath. Feel how light it seems, how weightless. But 1 cubic meter of air weighs about 1.2 kilograms. That means the atmosphere above you, stretching upward for miles, presses on your body with the force of a small elephant. Thankfully, your internal pressure pushes back equally, or you'd be a rather flat bit of art on the floor. Scientists still debate how ancient humans first conceptualized air. Some ancient Greek thinkers called it one of the 4 elements. In China, qi represented the life force that flowed invisibly. Both were wrong chemically, yet somehow right emotionally. Even today, when you take that deep, satisfying inhale, you're participating in the oldest ritual life has. And the air isn't uniform. The scent of the sea carries salt particles and dimethyl sulfide from plankton blooms. Mountain air contains extra ozone from high-altitude reactions. City air is laced with traces of hydrocarbons and caffeine molecules escaping coffee shops. The world's atmosphere is like one gigantic, slow-moving cocktail shaker, constantly blending, diluting, reacting. Somewhere above the Pacific, a molecule exhaled by you tonight might eventually brush past the petals of a cherry blossom in Japan. That's not poetic exaggeration, it's diffusion, the slow wandering of molecules that turns the world into one shared lung. Here's a quirky tidbit. Every breath you take probably contains at least 1 atom of nitrogen that once passed through Julius Caesar's lungs. Statistically inevitable, the math checks out. You're literally breathing ancient history. So when you yawn tomorrow morning, remember, you're sharing air with emperors, dinosaurs, and the occasional medieval alchemist. You glance at the faint shimmer above a candle flame, where convection makes the air ripple like a mirage. That's the only time you really see air, when temperature bends light enough for your eyes to notice. Otherwise, it hides in plain sight. But invisibility doesn't mean absence. It just means perfect balance. Molecules so small, fast, and evenly spread that your senses can't separate them. The universe's finest camouflage, even silence, depends on air. Without it, there'd be no sound, just the eerie hush of vacuum. The next time you whisper into the darkness, remember that it's chemistry that carries your voice. Vibrations of nitrogen and oxygen bumping their way across space to another ear. Invisible matter, invisible communication. Somewhere outside, the wind stirs the leaves. You can't see what's moving them, but you can hear and feel its presence, the result of pressure differentials, friction, and the restless kinetic energy of 1 trillion invisible partners. You're never truly alone. You're surrounded, embraced, and sustained by this transparent, ceaseless ocean. Take one last slow breath for tonight. Inhale the invisible. Let it remind you how the simplest things, the ones you can't see, often do the heaviest lifting. And as you exhale, picture your molecules joining the endless drift, rising, mixing, maybe brushing past another dreamer somewhere far away who's doing exactly the same thing. The room feels still, but stillness is a lie. Nothing ever truly stops moving. Around you, in every cubic centimetre of air, billions of molecules are colliding, reacting, exchanging partners in a microscopic frenzy that never rests. The chemistry of the invisible isn't static, it's a restless play, where each atom improvises its next step. You probably imagine reactions as something confined to test tubes and lab benches, but you're living inside one right now. The entire atmosphere is an enormous slow-motion experiment, constantly remixing itself through colourless reactions that sculpt everything from rust to breath. If you could see these reactions, the world would shimmer like heat haze. Oxygen molecules would occasionally bump into nitrogen oxides and form ozone. Water vapour would cling to microscopic dust grains, birthing tiny droplets. Carbon dioxide, endlessly exhaled by you and billions of others, would drift and merge with light, heat, and plant leaves entering cycles older than language. The quiet around you hums with invisible exchanges, electrons hopping, bonds twisting, energy shifting hands faster than you can blink. A single spark could make the invisible suddenly visible. Combustion, the most dramatic of these reactions, turns unseen gases into heat and light, but most chemical transformations are gentler, quieter. Oxidation, for example, happens right under your nose every moment. The metal in your lamp base slowly steals oxygen from the air, trading a bright sheen for a dull crust of oxide. That's rust, a slow fire that burns without flame. In fact, the chemistry of rust and the chemistry of your breath are cousins, both driven by oxygen's hunger for electrons. If oxygen were a person, it would be that friend who can't stop borrowing things and never gives them back. This appetite is ancient. Long before human eyes watched metal corrode, invisible oxidation sculpted entire worlds. Early Earth's rocks reacted with atmospheric oxygen and turned red, staining the planet's surface with iron oxides, the same chemical fingerprints you find on Mars today. Historians still argue whether that great oxidation event, about 2.4 billion years ago, was sudden or stretched over eons. Either way, it changed the chemistry of everything alive. The invisible became transformative, shaping the colour of stone and the possibility of breath. Even your body is a slow, living example of colourless chemistry. Oxygen seeps into cells, meeting glucose in tiny furnaces called mitochondria. There, without flame or flash, carbon atoms split and rearrange, forming carbon dioxide and water. Energy flows out, invisibly lighting up the body's molecular cities. The warmth you feel on your skin isn't magic, it's just invisible oxidation done neatly and quietly. Every heartbeat, every thought, every blink is powered by reactions you'll never see. You're a walking chemistry set with excellent branding. Outdoors, the invisible gets rowdier. Sunlight hits molecules high in the sky, splitting them, charging them, driving reactions that ripple through air and water. When ultraviolet rays strike oxygen, they form ozone, a molecule so reactive it can clean surfaces, sterilize rooms, or, in high enough concentration, burn your lungs. Yet in the stratosphere, ozone's hunger for UV light shields you from radiation. Same molecule, different context. Nature loves irony. There's a kind of rhythm to these unseen exchanges. Picture the air like an orchestra of collisions, each note a transfer of energy. Sometimes, an excited molecule releases that energy as light, giving rise to faint chemiluminescence, the ghostly glow of a decaying plankton bloom, or the eerie green shimmer of foxfire on damp logs. Ancient travellers seeing that glow in forests thought spirits lingered in the trees. The truth, of course, was chemistry. Luciferin molecules reacting with oxygen, releasing photons as they relaxed. Invisible until it wasn't. And sometimes the invisible is personal. The faint metallic tang you taste after touching coins. That's a reaction between the oils in your skin and the iron in the metal, forming tiny volatile compounds that mimic the smell of blood. The world constantly writes itself in chemistry, and your senses only catch the faintest edge of the story. You're like someone listening to an orchestra but hearing just one instrument at a time. If we zoom into where electrons dance, the picture gets stranger. A simple molecule of hydrogen peroxide sitting on your bathroom shelf might look innocent, but even as it rests, bonds are vibrating, flexing, preparing for release. When it decomposes, it forms water and oxygen gas, but the process is self-driven. No colour change, no smell, just silent rearrangement. Early chemists thought reactions required visible drama, but the invisible ones turned out to be the most universal. You're surrounded by them in the air, in your food, even in the slow chemical whisper of decay that turns fallen leaves into soil. There's one invisible reaction that never stops: carbon dioxide dissolving into water, then slipping back out. Every time rain falls through the air, it carries a little CO2 with it, becoming mildly acidic. That gentle acidity shapes mountains, dissolving stone grain by grain. Over millions of years, entire landscapes melt invisibly under that quiet chemistry. No explosion, no storm, just the persistent colourless patience of carbonic acid doing its work. You could call it the most polite form of destruction. And then there's the invisible chemistry of smellless fire. Deep within your own cells, enzymes catalyze reactions at lightning speed without a spark. Each enzyme is like a tiny matchmaker coaxing molecules into relationships they'd never form alone. You might say enzymes and diamines and the introverts of chemistry. Quiet, efficient, and doing all the work while someone else takes the credit. One quirky tidbit. During the 18th century, scientists tried to weigh air before and after burning substances, expecting to find a loss. Instead, the material gained weight. It was a shock. Something invisible from the air had joined the solid. That revelation helped disprove the phlogiston theory and opened the door to understanding oxidation. So yes, once upon a time, humanity had to learn that invisible things could actually make stuff heavier. That's the kind of plot twist nature likes to pull. Modern chemistry still dances with the unseen. When lightning cracks across the sky, it briefly turns nitrogen and oxygen into nitrogen oxides, which rainwater later transforms into nitrates. Natural fertilizer falling from the heavens. Farmers in ancient times didn't know this, but they noticed crops flourished after storms. Today we know why. Invisible chemistry writing green miracles into soil. And yet even knowing all that, you still look around and see nothing. The human brain is wired to trust eyes more than molecules, which is why invisible chemistry feels like magic. You live inside a constant chemical storm and call it air. You sip invisible reactions through your lungs and call it breathing. You exhale the product of your own internal fire and call it peace. Right now, as you sit there, the molecules in your breath are reacting with others in the room. They'll linger for hours, maybe days, before drifting elsewhere. Somewhere a plant will split them apart again. You're part of a molecular relay, passing invisible energy down an endless line. The chemistry of the invisible connects everything, leaf to lung, ocean to sky, spark to storm. So maybe the next time you open a window, you'll imagine those unseen reactions spilling through the frame, swirling like ghost currents, reshaping themselves endlessly. You can't see them, but they see you in a way. You are one of their ongoing reactions, their living continuation. And though the air looks still, you'll know better now. Stillness is only what invisibility feels like from the outside. You take a long, quiet breath, and suddenly, it feels a little different now that you know how busy that simple act really is. You're no longer just inhaling, you're participating in a planetary trade agreement, a chemical handshake between air and blood. Every time your chest rises, an invisible transaction unfolds. Oxygen goes in, carbon dioxide goes out, and somehow that simple swap keeps you alive. The chemistry of breath is so subtle, so constant that you only notice it when it stumbles. But tonight we're slowing it down, tracing a single inhale through the invisible corridors of your body, watching it work its magic molecule by molecule. That first moment, when air brushes the inside of your nostrils, chemistry has already begun. The lining of your nasal passages warms and filters what you breathe, trapping dust and stray pollen, while water vapor adds just the right humidity. Each oxygen molecule that slips past your sinuses carries with it a small story. Born from a leaf's photosynthetic machinery released into the air, drifted through clouds and cities, and finally, lucky thing, found its way to you. You inhale roughly 10,000 litres of air every day, which means the chemistry of your lungs is constantly negotiating with the atmosphere like a very polite customs officer. Inside your trachea, the air divides and subdivides, down bronchi and bronchioles until it reaches the alveoli, the delicate bubbles at the end of the road. If your lungs could be flattened out, their surface area would cover a tennis court. Every one of those microscopic air sacs is lined with a thin film of moisture, where gases meet across a barrier only 2 cells thick. It's here that oxygen dissolves into the liquid layer, slipping past cell membranes like a ghost through walls. On the other side waits hemoglobin, the red protein chauffeur that never rests. Hemoglobin doesn't just carry oxygen, it negotiates with it. Each molecule has 4 iron atoms, and each of those combine 1 oxygen molecule, forming a reversible partnership. It's an elegant design. Hemoglobin clutches oxygen tightly in the high concentration of your lungs, then gently lets go in the lower concentration of your tissues. The chemistry follows something called the oxygen dissociation curve, an invisible balance between holding and releasing. You could call it the Goldilocks principle of respiration. Not too clingy, not too distant, just right. There's something almost romantic about it. If you squint, oxygen binds to iron, forming a temporary union. And as blood flows through capillaries, carbon dioxide and hydrogen ions subtly change hemoglobin's shape, encouraging oxygen to leave. It's a quiet breakup at the molecular level, and the moment oxygen departs, it joins a biochemical waltz of combustion, though the fire burns cold and invisible. Inside your cells, oxygen meets glucose and enzymes carefully guide them through dozens of steps known as cellular respiration. The end result energy are water and carbon dioxide. The visible world runs on invisible chemistry. Historians still argue whether the discovery of hemoglobin's function in the 19th century owed more to the physics of light or the patience of chemistry. It was through spectroscopy, shining light through blood, that scientists realized oxygen changed the absorption spectrum, subtly altering its color. In other words, your very blood glows differently depending on its chemistry. That's not poetic license, it's measurable physics. The red of life isn't static, it's the visible echo of invisible reactions. Here's a quirky detail. The average red blood cell makes about 250,000 round trips through your body before it's retired, carrying oxygen molecules that will never meet again. When the cell is finally broken down in the spleen, the iron from its hemoglobin is recycled to make new ones. Nothing wasted. Every breath you take borrows atoms that have already served in millions of other lungs. You're breathing recycled stardust and ancient life. Oxygen itself first appeared in abundance when photosynthetic bacteria flooded the atmosphere billions of years ago. Back then, it was poison to most forms of life. Ironic, since now you depend on it. Evolution's sense of humour runs deep. As you exhale, carbon dioxide leaves the bloodstream, but it doesn't just drift away as a spent gas. Roughly 10% of it stays dissolved in plasma, balancing blood pH. Another fraction binds temporarily to hemoglobin, while the rest forms bicarbonate ions in a clever reversible reaction catalyzed by the enzyme carbonic anhydrase. The name sounds like something you'd find in a comic book. But without it, you wouldn't last minutes. It's the reason your blood can carry carbon dioxide efficiently, and it works invisibly, without fanfare, millions of times per second. This exchange, oxygen for carbon dioxide, is constant, rhythmic, and stuntant. Yet when something disrupts it, the consequences appear instantly. At high altitude, where air pressure drops, each breath brings fewer oxygen molecules. Your body compensates by producing more red blood cells, a slow adaptation that climbers feel as both exhilaration and exhaustion. Down at sea level, carbon monoxide, an invisible odorless gas, can slip into hemoglobin's seat, binding to 200 times more tightly than oxygen. It's a chemistry lesson with fatal stakes, a reminder that even invisible molecules can outsmart you. You probably think of exhaling as the end of the story, but it's really the beginning of another. That carbon dioxide joins the atmosphere, where plants inhale it through stomata, tiny pores that open and close with sunlight. Inside their chloroplasts, the reverse of your own chemistry unfolds. Carbon dioxide becomes glucose, oxygen is released. The entire biosphere runs on this invisible exchange, this global duet between breath and leaf. Every living thing participates, one side exhaling what the other inhales. The world is a single lung and you're part of its rhythm. If you could visualize it, your breath would look like mist spreading through the room, warm, moist, heavy with invisible water and carbon dioxide. Within minutes, it would disperse into the air indistinguishable from all other molecules. A breath you take now could linger for weeks, perhaps years, drifting across continents before joining another organism's lungs. Some of your exhaled atoms may someday feed an oak tree, dissolve in ocean water, or even freeze in a polar ice cap. That's chemistry's quiet promise. Nothing truly disappears, it only changes partners. And there's another invisible marvel at work. Every inhale subtly alters your mood and alertness. The brain's chemistry is tuned to carbon dioxide levels. When they rise, breathing quickens, and when they fall, you relax. Yogis and meditators have known this intuitively for millennia, practicing breath control long before the biochemistry was understood. Historians still debate whether ancient pranayama practices arose from spiritual intuition or from practical observation of oxygen's effects, but either way, they mapped the invisible chemistry of calm long before science caught up. Now take another breath, slow, deliberate. Imagine watching those oxygen molecules travel from nose to lung, from lung to blood, from blood to cell, and finally to the very mitochondria that keep you warm. The air you drew in seconds ago has already become part of you, and soon it will leave as something else entirely. Invisibility, in the end, isn't absence, it's transformation. The chemistry of breath proves that unseen doesn't mean unreal. You're built on invisible exchanges, powered by invisible reactions, and sustained by invisible partnerships that have been running smoothly for billions of years. So that the next time you sigh, maybe you'll remember what's really happening. A soft orchestration of molecular trades, each one carrying the quiet hum of life. You can't see it, but you can feel it. And maybe that's enough proof that chemistry, even invisible chemistry, has always been the most intimate science of all. You lean back and feel the faint warmth of light against your skin, the quiet, invisible sort that never quite announces itself. What looks like gentle daylight is actually a stream of energy spanning a spectrum from violet to far beyond red, most of it unseen. You live wrapped in radiation you cannot perceive, a subtle glow from the cosmos and the sun that sculpts weather, growth, and even your mood. It's strange, isn't it, that something invisible could define so much of what feels tangible. The chemistry of light is a trickster, translating unseen wavelengths into colour, warmth, and life itself. Visible light is just a narrow slice of the electromagnetic spectrum, a sliver between 400 and 700 nanometers wide. That's what your eyes can detect. But surrounding that rainbow is an ocean of other frequencies. Ultraviolet, infrared, microwaves, gamma rays. You're bathing in them all the time. The infrared from your skin keeps you cozy under blankets, while ultraviolet waves from the sun quietly rewrite the DNA in your cells. The world glows with invisible chemistry, and your body is both participant and shield. Sunlight doesn't simply shine, it reacts. When ultraviolet light hits your skin, molecules of 7-dehydrocholesterol absorb the energy, breaking and reforming bonds to become vitamin D3. That invisible reaction is one of the few ways your body makes a vitamin from scratch. Without it, your bones would weaken and your immune system would falter. The irony, of course, is that the same ultraviolet light can also damage DNA, causing the mutations that lead to skin cancer. Historians still argue whether ancient societies that worship the sun were responding to its visible brilliance or to the invisible vitality it bestowed. Either way, those early instincts weren't wrong. The sun really is a chemist. You probably protect yourself from its enthusiasm with sunscreen, and here's where the invisible gets even sneakier. Sunscreen molecules like avobenzone and zinc oxide absorb or scatter ultraviolet photons before they reach your DNA. Each particle performs a tiny chemical conversion, transforming high-energy light into harmless heat. You can't see it, but with every application, you're coating yourself in a field of molecular mirrors. Ancient Egyptians did something similar 3,000 years ago, grinding crocodile dung and rice powder into a paste that reflected sunlight. Modern chemistry, thankfully, smells better. Infrared, meanwhile, slips through the scene quietly. It doesn't change DNA, but it stirs motion instead, making molecules jiggle faster. That's what warmth really is, molecular vibration. When you feel the sunlight on your face, even after the visible rays have passed behind clouds, you're feeling infrared chemistry. Infrared photons are like gentle persuaders. They convince water, carbon dioxide, and other molecules to vibrate in specific patterns. The greenhouse effect that keeps the planet livable is, at heart, an infrared conversation between Earth and its atmosphere. Without those invisible vibrations, the average global temperature would hover below freezing. You'd need a parka to step outside in summer. Sometimes, invisible light makes itself known through colour created indirectly. The deep blue of the sky is a byproduct of Rayleigh scattering, tiny molecules in the atmosphere bouncing short wavelength light more efficiently than long. The red of a sunset, conversely, is light filtered through more air, where blue has been scattered out. You never see the photons themselves, only their side effects. The sky, in essence, is a canvas painted by invisible physics. There's something beautifully deceptive about this. Plants, for instance, see light differently. Their chlorophyll absorbs red and blue photons but rejects green, which is why leaves appear that colour to you. Yet beyond your sight, in the near-infrared range, leaves glow brightly to instruments designed to detect it. Farmers and satellites rely on that invisible fluorescence to gauge plant health. So while you admire a forest for its visible beauty, a camera tuned to the right wavelength would see it as radiant beyond imagination. A quirky tidbit. During World War II, pilots discovered that some materials glowed faintly under ultraviolet light, helping identify enemy planes. Later, chemists found that quinine in tonic water fluoresces the same way. It drinks invisible UV and spits out visible blue. So every time your drink glows under a blacklight, You're watching invisible light translated into visible laughter. The universe has a sense of humour too. Even your mood owes something to the invisible spectrum. On dark winter days, a lack of bright light lowers serotonin production, nudging you toward lethargy. Meanwhile, too much bright light, especially the blue wavelengths from screens, suppresses melatonin, the hormone that whispers sleep. You're wired to the chemistry of light whether you acknowledge it or not. Some scientists now experiment with narrowband lighting that mimics dawn's spectrum to reset human circadian rhythms, essentially using invisible hues to tune biology. Historians still debate whether ancient firelight flickering warm and orange was not only a comfort but also an evolutionary sleep aid, conditioning our brains to rest beneath its spectral lullaby. Step outside on a clear night, and the invisible deepens. The starlight reaching your eyes began as nuclear reactions millions or billions of years ago, photons born from atoms colliding inside suns. Many of those photons fall outside visible range, but some slip through perfectly tuned for your retinas. When astronomers point infrared telescopes at the sky, they see cold gas clouds glowing where no visible star appears. Chemistry continues there, unseen. Hydrogen atoms merging, dust absorbing light, molecules forming in silence. The universe is mostly dark not because it's empty, but because your eyes catch only a fraction of its conversation. Invisible light is everywhere in modern life too. Remote controls speak in infrared pulses. Fiber optic cables hum with laser light that no human can see, but that carries entire worlds of information. Airport scanners use terahertz radiation to peer through fabric, while MRI machines map atoms by their radio responses. The 21st century runs on light that hides from sight. You reading or listening to this are probably bathed in Wi-Fi signals, Bluetooth waves and background microwave radiation left over from the Big Bang, a faint afterglow of creation whispering through every atom. The chemistry of invisible light ultimately is a story of translation. Molecules absorb energy, shift, release it differently, and the universe becomes visible for an instant before fading again. Your body participates in that translation every second. Retinal molecules in your eyes change shape when hit by photons, triggering nerve signals that your brain interprets as colour. Those same molecules reset themselves, ready for the next flash. Seeing, in chemical terms, is nothing more than an endless series of photoreactions, light turned into thought. You close your eyes now and still feel light through your eyelids. A dim warmth that proves invisibility doesn't mean absence. It's there, coursing through you, guiding circadian chemistry, fueling vitamin synthesis, whispering to your cells when to rest and when to rise. The next time you step into daylight, remember, the invisible is painting you constantly, one photon at a time, with chemistry too fast to see but too important to ignore. You exhale slowly, and for the first time tonight, you notice the faint shimmer of your own breath in the cool air, a ghostly mist that vanishes almost as soon as it appears. It's easy to forget that dry air is never truly dry. Suspended all around you are invisible water molecules, constantly dancing, colliding, clumping and separating again. You live in a permanent fog, too thin to see, too essential to escape. The chemistry of vapour is the quiet heartbeat of weather, of comfort, of life itself. Without it, every inhale would feel like paper scraping your lungs, and every leaf would wither under a sun that no longer knew how to rain. Each molecule of H2O is tiny, so small that about 33 sextillion could fit inside a single thimble. They drift freely yet rarely alone. Most are attached in fleeting hydrogen bonds, momentary handshakes between neighbouring molecules. They hold each other just long enough to pretend they're solid before letting go to flow as liquid or soar as vapour. The dance is ceaseless. In every second, some molecules near you evaporate while others condense. Equilibrium isn't stillness, it's a balancing act performed by trillions of unseen performers. When water evaporates, it steals heat. That's why your set feels cooler when sweat dries. The departing molecules absorb energy to break free from their liquid prison. Conversely, when vapour condenses, it releases that same energy, warming the surrounding air. This invisible energy exchange is what fuels hurricanes, thunderstorms and gentle morning fog alike. The global weather machine runs on chemistry you can't see but can absolutely feel. Imagine following a single molecule from the ocean. The sun's infrared radiation hits the surface, shaking it loose. It rises, invisible, carried out by convection currents, until the air cools and can no longer hold so much vapor. Then, click, the molecule joins others around a speck of dust, forming a microdroplet. Multiply that by 1 trillion and you have a cloud. A single cubic meter of cloud contains more than 100 million droplets, each less than 1/100th of a millimeter wide, suspended by the gentlest upward air currents. To the naked eye, it looks like a soft cotton puff. To chemistry, it's a floating factory of phase changes. Historians still argue whether the ancient Greeks or the Chinese first theorized about the cycle of water, evaporation, condensation, precipitation. But what matters is that long before satellites, humans intuited this invisible loop. Medieval alchemists saw clouds as proof that transformation was possible. Vapor becoming liquid, air becoming water, matter shifting states yet keeping its essence. In a sense, every raindrop is an ancient alchemist's dream made real. Here's a curious thought. The air in your room contains enough water vapor to make a small cup of liquid water if condensed. It doesn't feel humid, but humidity hides in numbers. At room temperature, each cubic meter of air can hold up to 18 grams of water vapor. That's about 3 teaspoons. When you boil a pot of water, you're not adding something new to the air, you're simply letting invisible become visible. Steam is just vapor meeting cooler air, condensing into droplets big enough for your eyes to catch. That same transformation plays across your breath. When you breathe out on a cold morning, the warm moisture from your lungs meets the chilly atmosphere and condenses into visible mist. It's your internal humidity briefly revealed, a personal weather pattern in miniature. Each exhalation paints a fleeting portrait of equilibrium. The invisible turned visible, then gone again. Humidity does more than make hair misbehave. It shapes your comfort and even your perception of temperature. High humidity slows sweat evaporation, making heat feel heavier. Low humidity lets moisture flee too fast, drying skin and throats. Ancient desert travelers knew this instinctively. Some carried small ceramic jars wrapped in damp cloth. As the water in the cloth evaporated, the jars cooled, preserving precious liquids. Evaporative cooling, a trick of invisible chemistry, kept civilizations alive long before refrigeration. A quirky tidbit from the history of water. In the 18th century, scientists debated whether vapor was an element or a fire-air mixture. It wasn't until the early 19th century that John Dalton's atomic theory clarified the idea that vapor is simply water in gas form. His insight bridged meteorology and chemistry, showing that clouds weren't mystical but molecular. Yet even today, the physics of condensation, how droplets decide when to form, why some clouds rain while others don't, remains partly mysterious. Meteorologists still argue whether microphysical turbulence or dust composition plays the dominant role. The invisible resists total comprehension. Vapor's presence also writes chemistry into your walls, books, and lungs. Too little humidity and wooden floors shrink, too much and mold spores awaken from dormancy. You might not see them, but these fungal chemists are always waiting for their cue. A bit of moisture, a hint of warmth. In old libraries, curators keep humidity steady, not just for comfort, but to prevent ink from bleeding and parchment from crumbling. The invisible chemistry of vapor quietly guards history itself. There's another form of ghost water, the microscopic film that coats every surface, even the driest desert rock. Molecules of water cling to minerals through hydrogen bonding, forming a layer only a few atoms thick. This thin veil allows chemical reactions to occur that otherwise couldn't. Metals corroding, salts crystallizing, life persisting. Scientists have found bacteria surviving in these films, living at the very edge of invisibility. You could say that where vapor lingers, life finds a loophole. And then there's the astonishing chemistry of dew. Late at night, when surfaces cool faster than the surrounding air, water vapor condenses into droplets. Each bead of dew is a tiny archive of the night's temperature and humidity. Ancient farmers read dew as a weather forecast. A heavy fall meant clear skies ahead. The process seems simple, but it's molecular poetry, hydrogen bonds whispering together, deciding to rest. You close your eyes and imagine the world's invisible humidity, connecting oceans, clouds, and breaths in one continuous flow. The water you drink today may once have drifted as vapor above a prehistoric forest or condensed on the skin of a mammoth. In every molecule of water, time folds, past and present held together by chemistry too small to see. The next time you see fog rolling across a field or breath misting in winter air, remember that you're witnessing the border between visible and invisible. Vapor isn't absence or presence, it's both, shifting faster than thought. You live inside that transformation, breathing it in, exhaling it out, part of the endless cycle that turns oceans into clouds, clouds into rain, and rain back into ocean again. The invisible water around you is never still, it's always moving, always changing, always whispering its story in silence. You stretch your fingers, maybe flex a shoulder, and somewhere deep within the soft machinery of your body, a spark leaps invisibly from one cell to another. No thunder, no flash, just a whisper of electricity that sets muscles contracting, neurons firing, thoughts forming. It's easy to forget that the chemistry of life runs on charge, that your every move, emotion and idea begins as the rearrangement of ions so small you could fit 100 billion of them on a pinhead. The hidden electricity of life isn't a metaphor, it's the most literal form of energy you possess, humming constantly beneath the skin. Inside each nerve cell, the world is divided by a delicate membrane, separating salty fluids rich in sodium, potassium and chloride. This boundary holds a charge difference of about 70 millivolts, a tiny battery, yet powerful enough to transmit information at lightning speed. Every time a neuron fires, sodium ions rush in, potassium ions flow out, and a pulse of voltage ripples down the axon. To you, that pulse might feel like a thought, a twitch, or a heartbeat. To chemistry, it's nothing but the brief dance of ions chasing equilibrium. The phenomenon was first measured in the early 20th century using a giant squid's nerve fibre, large enough to insert electrodes without destroying it. Historians still argue whether that was brilliant foresight or sheer luck, but those experiments unlocked the electrical code of biology. They showed that life isn't just chemical reactions bumping around aimlessly. It's a precisely wired network where chemistry and electricity are two sides of the same coin. Your heart, for instance, beats because of this invisible current. Specialized pacemaker cells in the sinoatrial node generate rhythmic electrical impulses that spread through cardiac tissue, triggering contraction. Every lub-dub you feel is the sound of chemistry obeying the laws of physics, translating ionic shifts into motion. And the heart's electric song can be recorded as an electrocardiogram, a trace of voltage spikes so subtle you'd miss them without the right tools. Each wave on that screen is a record of your inner lightning. A quirky tidbit: frogs' legs twitching after death once convinced scientists that electricity was the vital force animating all creatures. In the late 1700s, Luigi Galvani noticed that touching a metal scalpel to a dissected frog's nerve made the muscles jerk. His contemporary, Alessandro Volta, disagreed. It wasn't a mystical life current, he said, but a chemical reaction between metals producing electricity. Their friendly feud gave birth to two new sciences, electrophysiology and the battery. Your phone, in a sense, owes its existence to a dead frog's leg. Every nerve impulse you send, every thought you have, is an echo of that same principle. Chemical energy becoming electrical, then back again. At the synapse, where one neuron meets another, the signal briefly leaves the realm of voltage and enters the realm of molecules. Neurotransmitters like dopamine, serotonin, and acetylcholine spill into the tiny gap, bind to receptors, and trigger new electrical waves in the next cell. It's chemistry writing electricity in invisible ink. You never feel this transaction directly, but it's happening millions of times a second as you listen, breathe, or drift towards sleep. The balance of these invisible ions also governs mood. Too little serotonin, and neurons miscommunicate. Too much potassium outside cells, and the heart stumbles in its rhythm. The chemistry of happiness, sadness, and anxiety, all of it relies on maintaining the quiet charge difference across cellular membranes. Some modern antidepressants work by keeping serotonin molecules in the synapse longer, adjusting the flow of messages just slightly. Microscopic tweaks to invisible currents become emotional weather systems in the mind. Electricity also drives motion on a larger scale. When you reach for something, motor neurons send voltage down long axons toward muscle fibers. There, calcium ions surge from storage sacs, binding to proteins called troponin and tropomyosin. The result? Myosin heads grab actin filaments and pull, your muscle shortens, your hand moves. It's chemistry and perfect choreography, an atomic-level tug-of-war that produces grace. The energy for this comes from ATP, the body's rechargeable molecule of choice, constantly rebuilt by cellular respiration. Every motion is powered by invisible sparks consuming invisible fuel. Some creatures have mastered the art of bioelectricity far beyond human scale. Electric eels, for instance, stack thousands of specialized cells called electrocytes, each generating a tiny voltage. Together, they can unleash shocks of up to 600 volts, enough to stun prey or startle curious scientists. Historians still debate whether ancient Amazonian fishers, who reportedly used eels to numb wounds, were early pioneers of electrotherapy or simply very brave. Either way, nature understood ion chemistry long before we did. Your own body glows faintly with electrical activity, though too weakly for eyes to see. Sensitive instruments can detect tiny electromagnetic fields around your heart and brain, fluctuating with every heartbeat and thought. Some researchers explore whether these fields subtly influence nearby cells, a debate that continues in modern bioelectromagnetics. The idea that invisible electrical whispers might help wounds heal or guide embryonic growth sounds like science fiction, yet evidence quietly accumulates. Perhaps once again, invisibility hides importance. You might laugh, but even your bones generate small electric currents when stressed. As you walk or run, the deformation of bone crystals creates piezoelectric signals that stimulate repair and growth. Every step you take sends microscopic lightning through your skeleton, reminding it to stay strong. The phrase "use it or lose it" turns out to be electrochemical advice. Then there's the invisible voltage of the Earth itself. Lightning is only the loudest expression of a constant global circuit connecting ground to sky. Your body, conductive and iron-rich, is part of that system. When you stand barefoot on soil, electrons from the ground subtly equalize with your skin surface, what modern enthusiasts call earthing. Historians still argue whether this practice's benefits are biological or psychological. But the chemistry is undeniable. You are electrically alive in an electrically active world. In every corner of existence, charge seeks balance. The same rule that powers your neurons also drives storms, magnets, and solar flares. Life, it seems, found a way to borrow that universal principle for thought. Every idea you have, every spark of imagination, is, quite literally, a spark. Now you sit there, maybe still as stone, but within you, trillions of ions are migrating, thousands of neurons are firing, and millions of molecules are rearranging themselves at the speed of electricity. The air hums softly in your ears, your pulse beats quietly in your fingertips. All of it, all the sensations that remind you that you are here, are built on invisible charge. You can't see it. You can only feel its consequences, the movement, the warmth, the living current that carries you through the night. So take a deep breath, let your heart settle, and remember that every flicker of thought, every whisper of feeling is chemistry wearing the mask of electricity. The invisible isn't shunned, it's just speaking a language you've only begun to understand. The air around you is quiet now, yet the room is full of invisible stories told through scent. You inhale, and without realizing it, thousands of molecules slip into your nose, each carrying its own chemical fingerprint. Smell is chemistry turned personal, a molecular language that bypasses logic and whispers straight to memory. You don't just perceive odors, you relive them. The invisible chemistry of smell has more power over your emotions than sight or sound ever could. And tonight, you're going to wander through that unseen world nose first. Inside your nasal cavity, a narrow patch of tissue known as the olfactory epithelium stretches like a small chemical radar dish. Embedded within it are receptor neurons, about 400 different kinds in humans, each tuned to detect a particular molecular shape. When an odor molecule fits into one of these receptors, it's like a key turning in a lock, triggering a signal that races straight to the olfactory bulb in your brain. Unlike sight or touch, this pathway skips the cerebral editor that filters most sensory input. That's why a single whiff can summon childhood in an instant. Chemistry doesn't ask permission before it opens your memories. Historians still argue whether ancient perfumers were scientists or mystics. In the bustling markets of Mesopotamia 4,000 years ago, traders distilled cedar oil, myrrh, and frankincense without knowing the word molecule. They learned by nose. Egyptian priests embalmed the dead in aromatic resins, believing the sweet fumes guided souls to the afterlife. Modern chemists later discovered that many of those same resins contain natural antimicrobials, proof that invisible chemistry was working practical miracles long before science named it. You probably think smell stops at the nose, but the invisible trail continues deep into emotion. The limbic system, seat of pleasure, fear and nostalgia, lights up when odour messages arrive. That's why the smell of rain can soothe you faster than a meditation app. That scent, called petrichor, comes from two main chemicals, geosmin, produced by soil bacteria, and plant oils that seep out during dry periods. When rain hits, those compounds aerosolize into the air, tickling your nose with the smell of renewal. Invisible water meets invisible molecules, and suddenly you feel grounded again. Here's a quirky tidbit. Every human has a unique odour fingerprint, just like DNA. It's made of volatile organic compounds your skin releases, shaped by diet, hormones and microbiome. Dogs can identify people by this invisible signature, even after showers or clothing changes. Researchers once trained dogs to detect diseases like diabetes or certain cancers purely by scent, because illness subtly alters body chemistry. To an animal's nose, your metabolism is a constant broadcast tower of molecules. Pheromones add another layer to the invisible narrative. Though humans don't rely on them as heavily as other mammals, your body still emits tiny chemical signals that influence perception and attraction. Some studies suggest that women living together synchronize menstrual cycles partly due to airborne pheromones. Others dismiss it as coincidence. Historians still argue whether such subtle cues guided courtship rituals in early human tribes, or if it's mostly a modern romantic myth. Either way, you're still producing invisible messages right now, whether you like it or not. The chemistry of scent extends far beyond biology. Every aroma you enjoy is a blend of molecules in intricate balance. Coffee, for instance, releases more than 800 distinct compounds when brewed. One of them, 2-furfurylethiol, is responsible for that unmistakable roasted note that turns sleepy mornings into bearable ones. Chocolate owes its warmth to pyrazines. Fresh-cut grass smells green because of cis-3-hexanol, a molecule released by damaged leaves, essentially a plant distress signal. You find it soothing. To the plant, it's an alarm. Invisible empathy, shared through chemistry. The act of smelling itself is physically intimate. Molecules have to enter your body to be perceived. Every pleasant fragrance you notice has, in some small way, become part of you. When you walk past a bakery and your stomach rumbles, that's molecules of caramelized sugar and butter literally binding to receptors in your nose and sending electrical messages to your brain's hunger center. Invisible chemistry doesn't just make you remember, it makes you act. Sometimes it also protects you. The nose evolved as an early warning system. Sulfur compounds in rotten food, for instance, trigger disgust to keep you safe. Hydrogen sulfide, the culprit behind the rotten egg smell, can be toxic in high concentrations. But here's the fun paradox. In trace amounts, your cells actually use the same gas to regulate blood pressure and metabolism. The line between poison and necessity is razor thin, drawn by concentration and context, two of chemistry's favourite complications. Perfume makers, meanwhile, have turned invisibility into art. Modern fragrances blend natural extracts with synthetic molecules that have never existed before, notes of ozone, metal, even freshly printed books. The goal is to evoke emotion, not accuracy. A single drop might contain compounds derived from flowers that bloomed halfway around the world, chemically reconstructed in a lab. When you wear Sierra perfume, you're wrapped in invisible storytelling, your personal weather system of volatile molecules drifting around you. And then there's memory, the true domain of invisible scent. Psychologists call it the Proust effect, after the writer who described childhood flooding back with the smell of tea and Madeleine cake. Your brain stores smell memories alongside emotions, so that the same odour can comfort one person and unsettle another. The molecule doesn't care, it's impartial. Chemistry provides the spark. Meaning is what you add. If you could watch the air above a city, you'd see clouds of scent molecules mingling. Exhaust, rain, bakery steam, perfume, the faint sweetness of blooming trees. The atmosphere is one enormous diffuser constantly remixing human and natural chemistry. Even the sterile, clean smell after a storm is chemical, ozone and nitrogen oxides reacting with organic matter. Invisible doesn't mean pure, it just means complex beyond your eye's capacity. Right now, as you breathe quietly, hundreds of invisible compounds are entering and leaving you. The faint detergent from your clothes, a hint of your shampoo, perhaps the ghost of dinner hours ago, all of them combine into a subtle halo of chemistry. You are at this very moment both sensor and source, both participant and experiment. So the next time you catch a scent that stops you in your tracks, pause for a moment, inhale gently. Somewhere in that invisible swirl is a molecule that has travelled from flower, soil, ocean or flames straight into you. It may stay only a second, but its chemistry will linger in your brain far longer, an invisible bridge between matter and memory. And as you drift closer to sleep, know that even the air smells faintly different now, warmed by breath, by life, by you. You let your eyes rest on the dark, maybe a candle flickering somewhere off to the side, and you can't help but think about what fire really is. We call it light, heat, destruction, but at its heart, it's chemistry made visible. Fire is simply oxidation you can see, yet not all oxidation glows. In fact, most of it hums along invisibly, slowly, patiently transforming everything you touch without ever bursting into flame. Tonight, you're wandering through that quieter realm of invisible flames, of cold fires that shape decay, digestion, and life itself. A flame begins with molecules colliding at high speed, fueled by oxygen eager to steal electrons. The reaction releases energy faster than it can dissipate, so it leaps outward as heat and light. But if the same exchange happens slowly enough, the light disappears. Rust, for example, is just iron burning in slow motion. Each reddish flake of oxide on a forgotten nail is the footprint of invisible fire. If you could speed time up 1,000-fold, you'd watch it flicker like a candle. Historians still argue whether early humans first encountered fire from lightning, volcanic rock, or spontaneous spark. What's clear is that long before they tamed visible flames, they lived surrounded by invisible ones. Every breath they took was oxidation at work. Every piece of meat they digested was a controlled burn. Metabolism, the great cold fire, consumes sugars and fats as gently as rust consumes iron. You are, in a way, a walking ember, energy releasing molecule by molecule, just slowly enough to keep you alive. In your cells, that oxidation unfolds inside the mitochondria, where glucose and oxygen meet in a delicate waltz guided by enzymes. Electrons flow down a microscopic conveyor belt called the electron transport chain, producing water, carbon dioxide, and the universal currency of energy, ATP it is, combustion disguised as life. The process is so elegantly regulated that the temperature of your body rarely wavers more than a few degrees. Without that balance, you'd either freeze or burst into invisible flame. A quirky tidbit. Chemists once tried to measure how much energy a person produces and found that an adult at rest emits about the same heat as a 100-watt bulb. That's right, you glow with the brightness of a small lamp. Only your light is infrared, invisible to human eyes. Thermographic cameras reveal it easily, painting your outline in colours of heat. You are, in truth, always burning, just politely. Not all oxidation is beneficial. Sometimes rogue molecules steal electrons in the wrong place, creating what we call free radicals. These reactive species can damage DNA, proteins, and membranes, igniting tiny biochemical fires that age and weaken cells. Antioxidants, whether from your diet or your own enzymes, are the fire brigade, neutralizing radicals before they spread. Historians still argue whether early herbal medicine, with its emphasis on balancing humours, was an intuitive understanding of oxidative stress long before the term existed. Maybe they didn't know chemistry, but they recognized the burn. Nature, of course, never wastes a good reaction. Some of its most breathtaking spectacles are flames you can't see deep in caves or rotting woodlands. Faint glows appear, bioluminescence. Fireflies, glowworms, even certain fungi produce light not through heat but through chemical reaction. A molecule called luciferin reacts with oxygen under the guidance of an enzyme, luciferase, producing photons instead of warmth. To the eye, it looks like living firelight. To chemistry, it's simply oxidation rerouted toward beauty. Even decay, the slow return of matter to Earth, is a type of invisible combustion. When microbes digest dead leaves, they oxidize carbon compounds into carbon dioxide and water, releasing energy too small to warm your hands but enough to power life underground. Compost piles steam on cold mornings because trillions of bacterial furnaces are burning invisibly within. You might think of them as caretakers of the carbon cycle, tending the fire that never dies out, only changes form. There's another kind of cold fire, one that hums quietly in human invention: catalytic oxidation. The engine in your car or the furnace in your house uses catalysts, materials like platinum or palladium, to encourage fuel to react with oxygen more completely and cleanly. The reaction itself happens invisibly on the catalyst's surface, no spark required. In laboratories, similar catalysts help convert pollutants into less harmful gases, transforming invisible toxins through equally invisible chemistry. Sometimes the greatest flames are those that never flare at all. Even your emotions flicker with oxidation. Adrenaline, the fight-or-flight hormone, is synthesized through a chain of redox, reduction-oxidation reactions in the adrenal glands. When you're startled, it floods your bloodstream, raising heart rate, dilating pupils, priming muscles for action. You feel the burn of energy because you are, quite literally, burning faster. Once calm returns, other molecules sweep in to neutralize the excess. Your inner firefighter's at work again. The invisible fire extends beyond biology. In the atmosphere, slow oxidation transforms pollutants into new compounds. Methane, for example, reacts with hydroxyl radicals to produce water vapor and carbon dioxide, an unseen process that determines how long greenhouse gases linger. Even without above flames, the sky burns every second, reshaping itself molecule by molecule. The auroras, though they seem electric, are partly chemical too. Oxygen atoms excited by charged particles release their energy as ghostly green light. Invisible reactions momentarily visible. There's a strange comfort in knowing that fire isn't something outside you. It's within, constant and sustaining. You are kept alive by the same principle that powers stars, just moderated, softened, disguised as breath and warmth. The sun burns hydrogen. You burn carbohydrates. Both are acts of oxidation. Both are stories of energy-seeking balance. If you close your eyes now, you might feel the warmth rising from your own skin, the faint reminder of that ever-present flame. It hums quietly in your chest, glows invisibly behind your thoughts, and flickers gently through every heartbeat. The chemistry of oxidation has no boundaries. It creates, it destroys, it renews. The world, it turns out, isn't built of solid things, but of burning processes in slow motion. And you, warm, breathing, luminous in your own invisible way, are part of that endless fire. You wake to the faint morning haze beyond your window, that thin shimmer that looks like mist but isn't. The city hums quietly beneath it, engines whispering, chimneys sighing, exhaust curling upward to vanish into what seems like nothing. Yet nothing isn't what it seems. Those vapours are chemistry in motion, an invisible alchemy of gases and particles that shape the air you breathe. Pollution, for all its invisibility, is a master of disguise. Colourless molecules that rewrite clouds, shift climates, and sneak into lungs without ever showing their face. The chemistry of air pollution began long before factories. Early humans sitting around campfires were already conducting the first experiments in aerosol physics. Each puff of smoke carried microscopic carbon spheres, unburned hydrocarbons, and acidic vapours that would drift, mix, and settle onto soil and lungs alike. The only difference between ancient smoke and modern smog is scale. A campfire warms 10 people, a city of engines warms an atmosphere. You, just sitting there, are wrapped in their invisible consequences. Invisible pollutants come in many flavours. Nitrogen oxides, carbon monoxide, sulfur dioxide, each a molecule small enough to slip unnoticed past your defences. Nitrogen oxides form when combustion gets too hot, forcing nitrogen and oxygen from the air to react. In sunlight, they spawn ozone at ground level, an ironic twin to the ozone that protects us up high. Up there, it shields life from UV. Down here, it inflames lungs and stunts crops. Chemistry never promised to play fair. Then there are the particles, microscopic specks of soot, dust and metals so fine they hang in the air like invisible glitter. Scientists call them PM 2.5, shorthand for particulate matter less than 2.5 micrometers across. That's 1/30th the width of a human hair. You could fit hundreds across the period at the end of this sentence, and yet each one can travel deep into the alveoli of your lungs. Once inside, they don't politely leave. They react, inflaming tissue, altering blood chemistry, even nudging your cardiovascular system toward distress. You don't see them, but your cells do. Historians still argue whether the first great smog disaster was in London or ancient Rome. Roman writers complained of choking smoke from wood and coal fires 2,000 years ago, but London's Great Smog of 1952 was impossible to ignore. For 5 days, sulfur dioxide from coal burning mixed with fog, creating a thick yellow haze that killed thousands. The chemistry was brutally simple. Sulfur plus oxygen plus moisture equals sulfuric acid, a corrosive mist that scoured lungs and stone alike. Modern air may look cleaner, but the invisible culprits have only become smaller and subtler. A quirky tidbit: every car engine is a miniature chemistry set performing thousands of reactions per second. Fuel molecules like octane break apart under heat, combining with oxygen to form carbon dioxide and water, but never perfectly. A few carbon atoms escape incomplete, becoming soot or carbon monoxide. Catalytic converters try to tidy the mess, using metals like platinum and rhodium to coax leftover gases into less harmful forms. It's invisible negotiation, chemistry working overtime to make the air breathable. Well, mostly. Some pollution isn't born from fire at all. Volatile organic compounds, VOCs, evaporate from paints, plastics, perfumes, even your cleaning products. They drift into the air, meet sunlight, and react with nitrogen oxides to form ground-level ozone and secondary aerosols. So while your lavender-scented candle feels pure, its chemistry may be whispering smog into existence. Invisible irony, courtesy of modern comfort. And yet, not all invisible pollution comes from humans. Volcanoes belch sulfur and ash, wildfires spew carbon, and even ocean plankton emit dimethyl sulfide, a gas that seeds clouds. The difference is one of balance. Nature's emissions ebb and flow with cycles. Human chemistry tends to add without pause. We've become the planet's most prolific atmospheric chemists, experimenting in real time with outcomes still uncertain. Scientists call it geoengineering by accident. The consequences extend high into the atmosphere. There, nitrogen oxides and chlorofluorocarbons, CFCs, once used in refrigerants and hairspray, rise to the stratosphere, where ultraviolet light breaks them apart. The chlorine atoms released act as catalytic agents, dismantling ozone molecules one by one. The discovery of the Antarctic ozone hole in the 1980s was humanity's first undeniable glimpse of invisible chemistry gone rogue. A few rogue molecules, harmless at ground level, had rewritten the sky. Thankfully, invisible chemistry can heal as well as harm. The global ban on CFCs through the Montreal Protocol became one of history's quiet triumphs. Since then, ozone levels have slowly recovered, a rare example of humans noticing an unseen problem and fixing it in time. Historians still debate whether the treaty succeeded because of scientific clarity or political luck, but the ozone's slow mending remains proof that invisible damage can be reversed, if we pay attention before it becomes visible. In the city, pollution's invisibility often lulls you into complacency. Clear skies don't mean clean air. Some of the most toxic pollutants are perfectly transparent. Carbon monoxide, for instance, binds to hemoglobin 200 times more tightly than oxygen, starving tissues while giving no sensory warning. A molecule with no colour, no smell, no taste, yet lethal by design. The chemistry of invisibility sometimes hides cruelty behind elegance. You might imagine that stepping into the countryside solves the problem, but even there, chemistry follows. Pesticide residues evaporate into rural air. Fertilizers release nitrous oxide, a greenhouse gas hundreds of times more potent than carbon dioxide. And distant pollutants drift across oceans and borders. The atmosphere ignores geography. What you exhale in one hemisphere can change the rainfall in another. Air, after all, is the ultimate global commons, shared, stirred and stirred again. Invisible though it is, pollution has colour in its consequences. Coral bleaching, melting glaciers, shifting weather, all trace back to molecules released unseen. Carbon dioxide, the quietest of them all, has altered the chemistry of oceans, turning them slightly acidic. Seashells dissolve faster. Reefs struggle to grow. The great invisible exchange between air and water now leans just enough off balance to rewrite ecosystem. And still, the air seems light and clear as you breathe it in. Maybe there's a hint of something metallic, maybe not. Invisible chemistry doesn't need your permission to work, it only needs time. But there's comfort too, in knowing that invisibility isn't invincibility. We've learnt to measure the unseen, to track molecules by their spectral fingerprints, to clean, to regulate, to restore. The same curiosity that caused pollution also invented filters, scrubbers, and renewable energy. Chemistry giveth, chemistry taketh away. So you stand by the window again, looking out at a world that seems calm, maybe even pure. Somewhere in that air are remnants of ancient smoke, modern exhaust, volcanic breath, and your own exhalation from last night. It's not pristine, but it's shared. One vast invisible medium connecting every living thing. Each molecule floating out there tells a story of reaction, resilience and return. You breathe it in, exhale it again, and become part of the endless chemistry of air. Sometimes clean, sometimes corrupted, but always alive. You look up, tracing the endless stretch of sky, and for a moment you can almost feel the weight of it pressing down. 100 kilometers of invisible chemistry stacked above your head. It's not just empty blue, it's an ocean turned upside down, layered in temperature, density, and composition. Tonight, you're going to drift through that unseen sea, rising higher and higher until air itself thins into near nothing. The atmosphere may seem like a single thing, but it's actually a delicate chemical gradient that shelters every living creature from cosmic indifference. Near the ground, in the troposphere, you're surrounded by familiar gases: nitrogen, oxygen, carbon dioxide, and a pinch of water vapor. Here, weather is born. Clouds build, rain falls, winds churn. But climb a little higher past the cruising height of planes, and chemistry changes its mood. The stratosphere begins, calm and layered, where ozone reigns supreme. Ozone, that 3-atom variant of oxygen, is both hero and hazard depending on altitude. Up here, it's the planet's sunscreen, absorbing ultraviolet radiation that would otherwise sterilize the surface. Down below, it's a pollutant that irritates lungs. The same molecule, two destinies. Chemistry loves irony. The formation of ozone is invisible drama. High-energy UV light splits ordinary oxygen, O2, into single atoms, each so reactive they immediately grab another O2 to form ozone, O3. These molecules then absorb more UV light and split apart again, creating a self-repairing cycle that turns lethal radiation into harmless heat. Without this fragile balance, DNA would unravel, forests would crisp, and life as you know it would never have left the sea. Historians still argue whether the first creatures to crawl onto land did so during a lull in solar intensity, or after the ozone layer thickened enough to permit it. Either way, invisible chemistry paved the path for every footprint since. As you drift higher, temperature oddly begins to rise again, sunlight absorbed by ozone warming the stratosphere from above. It's a counterintuitive detail that took scientists decades to understand. Early balloonists noticed that their thermometers stopped dropping past a certain altitude, but they couldn't explain why. Only later did chemists realize that invisible molecular reactions were heating the upper air. Every degree of temperature up there is proof of chemical energy converted from light. Above 60 kilometers, the mesosphere begins, a twilight region where air grows thin and meteors meet their fiery ends. Each shooting star you've ever wished upon is a pebble undergoing instant oxidation, glowing as it slams into oxygen molecules at supersonic speed. The fire you see streaking across the night isn't heat from friction, as old textbooks once claimed. It's chemistry. Atoms in the meteoroid react with atmospheric oxygen, releasing energy as light. You're watching metal burn in the world's highest bonfire. Climb higher still, and you enter to the thermosphere, where temperatures soar to hundreds or even thousands of degrees Celsius. Paradoxically, you wouldn't feel it. The air is so thin that there are too few molecules to transfer heat to your skin. Here, charged particles from the sun collide with oxygen and nitrogen atoms, exciting them until they emit visible light, the auroras, those green and red veils dancing over polar skies. Each ripple is a moment of invisible ionization suddenly made visible, chemistry performed in vacuum. Historians still debate whether the first observers of aurora thought they were divine messengers or weather gone mad. The Norse imagined Valkyrie riding through the sky. Chinese astronomers recorded heavenly dragons. What no one could have guessed was that those colours were electrons returning to calm after colliding with atoms hundreds of kilometres high. The aurora is an oxygen and nitrogen light show, painted by solar wind, powered by chemistry's quiet glow. A quirky tidbit: the upper atmosphere also forges new molecules that never touch the ground. In the mesosphere, cosmic rays bombard oxygen and nitrogen, creating fleeting compounds like nitric oxide and ozone dimers. Some of these descend slowly, influencing climate and weather far below. In a sense, every storm you feel might have been nudged by chemistry that began in space. The atmosphere's layers act as both cradle and filter. The troposphere keeps you breathing, the stratosphere guards you from UV, the mesosphere burns debris, the thermosphere deflects charged particles. Together, they're a chemical fortress held in delicate equilibrium by sunlight, gravity, and time. It's humbling to remember that every breath depends on reactions you can't see happening dozens of kilometers overhead. Even beyond the visible atmosphere, the chemistry continues. At the edge of space, atoms drift so far apart they can travel miles before colliding. Yet those rare encounters still matter. Hydrogen escapes into space, helium accumulates, and oxygen molecules occasionally meet solar radiation intense enough to tear them apart. The exosphere, Earth's outermost whisper, is the final chapter of the planet's invisible chemistry, where the atmosphere merges with the cosmos. Sometimes you can catch hints of this high chemistry from the ground. The purple tint of twilight, for instance, is caused by sunlight scattering through ozone and dust high in the stratosphere. After volcanic eruptions, aerosols injected miles up linger for years, reflecting sunlight and cooling the planet. The eruption of Mount Pinatubo in 1991 lowered global temperatures by about 0.5 degrees Celsius, a planetary chemical reaction playing out invisibly above the clouds. And yet, despite its complexity, the atmosphere remains fragile. Tiny shifts in gas concentration, carbon dioxide, methane, aerosols can tilt the entire system. Greenhouse gases trap infrared radiation, altering thermal balance. Chlorine atoms shred ozone. Soot particles seed or scatter clouds. The chemistry of the air is constantly negotiating with itself, improvising equilibrium anew each day. If you could rise high enough to look down, you'd see the planet wrapped in a faint blue halo, the rarely scattered glow of sunlight through gas. That halo is home. It's only a few atoms thick in cosmic terms, yet it holds every breath, every storm, every sunset humanity has ever known. You live at the bottom of a luminous ocean of molecules, your life supported by their invisible choreography. So the next time you look up and think of the sky as empty, remember it's anything but. Above you, nitrogen and oxygen spin, collide, react and protect. Ozone mends itself in the sun's rays. Auroras shimmer where chemistry meets electricity. And far beyond, the last wisps of air fade into the vacuum. Earth's invisible boundary drawn in molecules, not lines. You're inside it, breathing the product of billions of years of atmospheric chemistry, safe beneath the silent, unseen shield that keeps the universe at bay. You stand in the open air now, the night crisp, stars scattered overhead, and though you can't feel it, something is brushing through you, passing without sound, without light, without resistance. Invisible particles born from the decay of atoms and the fury of stars move effortlessly through your body by the trillions each second. You don't notice, but you are never untouched. This is the chemistry of radioactivity, the ghostly conversation between matter and energy that reshapes the universe atom by atom. It's invisible, unstoppable, and strangely elegant. The quiet physics of transformation written in chemical script. Inside every atom sits a small, dense heart, the nucleus. Most are content to remain what they are, but some are restless, unbalanced, yearning for stability. When they change, they release energy in forms you can't see. Alpha particles, beta rays, gamma photons, each one a messenger of invisible decay. It sounds menacing, but without radioactivity, the Earth itself would be cold and lifeless. The planet's core still glows with the heat of uranium, thorium and potassium breaking down, keeping magma molten and the magnetic field alive. Every sunrise, every compass point owes something to invisible nuclear chemistry simmering beneath your feet. Historians still argue whether Henri Becquerel's discovery of radioactivity in 1896 was accident or serendipity. He'd been studying phosphorescent uranium salts, expecting them to glow after sunlight exposure. Instead, he found they fogged photographic plates in total darkness. Invisible rays capable of penetrating paper and cloth were escaping from matter itself. Soon after, Marie and Pierre Curie isolated polonium and radium, substances that seemed almost magical, glowing faintly, warm to the touch, yet deadly in ways no one understood. They handled the salts barehanded. unaware that the invisible light within them was rearranging the chemistry of their own cells. And yet, radioactivity isn't just destruction, it's transformation. When an unstable atom emits an alpha particle, 2 protons and 2 neutrons, it literally changes its identity. Uranium becomes thorium, radium becomes radon. Beta decay does the same trick in subtler fashion, turning a neutron into a proton and an electron, shifting one element up the periodic table. You could say that atoms, like people, sometimes reinvent themselves by letting go of a little excess energy. The world is full of invisible radiation. The granite beneath your home may emit radon gas, the air carries traces of carbon-14, and bananas, yes, bananas contain potassium-40, a mild natural radioisotope. Every time you eat one, you add a pinch of radiation to your diet, though nothing dangerous. The human body itself glows faintly with radioactivity, its atoms constantly exchanging particles with the environment. You're not merely exposed to radiation, you're part of it. One quirky tidbit. During the mid-20th century, scientists discovered that fallout from atomic tests subtly altered the ratio of carbon isotopes in the atmosphere. Those isotopic fingerprints remain in tree rings, coral skeletons, and even wine vintages. For decades, experts could date a bottle of Bordeaux by its faint, invisible signature of bomb carbon. The chemistry of destruction became unintentionally a tool for art authentication. Only humans could turn apocalypse into inventory control. In medicine, invisible radiation performs miracles daily. X-rays, discovered by Wilhelm Röntgen just before Becquerel's work, revealed the skeleton without a single incision. Gamma rays from cobalt-60 kill tumours with precision, and positron emission tomography, PT scans, trace metabolism molecule by molecule using short-lived isotopes. Radioactivity, once feared as pure poison, now maps the living body in exquisite detail. It's still dangerous, but like fire, it becomes a servant when handled wisely. Historians still debate whether Marie Curie's early exposure shortened her life, or whether her constitution was simply too resilient to outlast the work. Either way, her notebooks remain radioactive to this day, stored in lead-lined boxes. She helped reveal that invisibility isn't emptiness, it's potential. In her words, nothing in life is to be feared, it is only to be understood. Few sentences summarize invisible chemistry better. Beyond Earth, radioactive decay is cosmic architect. Elements heavier than iron are born in supernovae and neutron star collisions, where unimaginable energies forge unstable isotopes that later decay into gold, uranium, and iodine. The warmth in your hand, the sparkle of jewellery, the salt in your tears, all trace their ancestry to atoms that once spat invisible radiation into the newborn universe. The cosmos itself is radioactive heritage. Even now, cosmic rays, high-energy protons and nuclei from distant galaxies, rain down constantly. Most pass harmlessly through the atmosphere, but occasionally they strike, creating showers of secondary particles that ripple through air and stone alike. At sea level, a few muons, a heavier cousin of the electron, zip through you every second. They arrive from events billions of light years away, reminders that the universe doesn't respect personal space, and yet we've learned to see the unseen. Geiger counters translate invisible impacts into clicks, cloud chambers reveal ion trails like ghostly comets, and scintillation detectors turn subatomic collisions into tiny flashes of light. Each instrument is a translator, giving voice to chemistry's quietest transformations. When you hear that staccato crackle of a Geiger counter near uranium ore, you're listening to atoms rewriting themselves. Of course, radioactivity has its darker legacy. From Hiroshima's blinding light to Chernobyl's silent fallout, humanity has tasted the destructive side of invisible chemistry. The invisible can wound more profoundly than the visible because it lingers, seeping into soil, bone, and memory. Yet even those tragedies drove new understanding: radiation ecology, safety protocols, and the realization that power demands humility. There's a strange comfort, though, in knowing that invisibility doesn't mean absence of purpose. Without radioactive decay, Earth would cool, magnetic fields would fade, and the planet's protective shield would vanish. Without carbon-14, we couldn't date ancient relics or trace lost civilizations. Without cosmic radiation, mutations, and by extension, evolution, would stagnate. Even danger has its role in the grand experiment. You take a slow breath, realizing that every atom of your body, every calcium crystal in your bones, every drop of potassium in your blood, was once forged in a star that ended in a burst of radioactive light. That glow still echoes through the universe and through you. The chemistry of the invisible isn't just around you, it's within you, humming quietly, keeping time with the cosmos. You are, in the most literal sense, radiant. So as you stand beneath the stars, let that thought settle. Energy never vanishes, it only changes hands. Somewhere a uranium atom splits, a star collapses, a medical scanner hums, and a cosmic ray passes through your chest. Invisible, yes, but never meaningless. The universe's quiet chemistry keeps unfolding, one particle at a time, unseen but unstoppable. You sit in the hush after midnight, that liminal hour when everything feels slowed, the air thick with the faint hum of stillness. But stillness, as you now know, is only an illusion. Even now, 1 billion invisible transactions are unfolding around you, molecules reacting, rearranging, helping other molecules react faster. It's the quiet kingdom of catalysts, the unseen accelerators that make chemistry happen on time. Without them, nearly every process in your body, your city, your planet would grind to a crawl. Tonight, we step into their invisible workshop where small things make big reactions possible. Catalysts are, in essence, chemical matchmakers. They don't get consumed, they simply encourage reluctant molecules to meet, react, and move on. A catalyst lowers the activation energy, the invisible hill that molecules must climb to change form. Imagine two shy atoms at a party standing apart. The catalyst walks over, introduces them, and steps aside once the sparks fly. That's chemistry's version of a good host. Without that nudge, reactions that should take seconds could take centuries. Inside your body, enzymes are the reigning royalty of catalysis. Each one is a protein folded into an intricate 3D maze that fits its target molecule like a glove. Lactase breaks down milk sugar, amylase turns starch into sugar, catalase dismantles hydrogen peroxide before it harms you. Without enzymes, your food would rot in your stomach instead of digesting. They are tiny biological timekeepers, ensuring every chemical step happens exactly when it should. The numbers are almost absurd. Catalase can process 40 million hydrogen peroxide molecules per second, neutralizing them into harmless water and oxygen. Blink once and your cells have just run a chemical assembly line faster than any human factory. Historians still argue whether early biochemists in the 19th century, who've described ferments in yeast and muscle, truly understood what they'd found. It took decades before scientists realized enzymes were not magic substances, but ordinary molecules doing extraordinary chemistry invisibly. A quirky tidbit. In 1897, a German chemist named Eduard Buchner accidentally proved that fermentation didn't require living cells at all. He crushed yeast, filtered out the liquid, and still produced alcohol from sugar. Life's chemistry, it turned out, could operate outside life itself. It was like discovering that music could play after the orchestra left the room. That single insight launched modern biochemistry, and all because an invisible catalyst refused to stop working. Catalysts don't belong only to biology. Every modern convenience you enjoy, from plastics to fuels to pharmaceuticals, exists because of invisible catalytic reactions. Inside oil refineries, massive beds of zeolite crystals crack long hydrocarbon chains into gasoline, guided by acid sites you could never see without a microscope. Platinum and palladium on your car's catalytic converter transform toxic carbon monoxide into carbon dioxide and nitrogen oxides into nitrogen gas. Without those invisible helpers, cities would choke in poison. Even the atmosphere relies on catalysis. High above, chlorine atoms from old CFCs act as destructive catalysts, breaking apart ozone molecules. A single chlorine atom can repeat the act thousands of times before being neutralized. Down below, nitrogen oxides in car exhaust serve as catalysts for smog formation, accelerating the creation of ozone at ground level. Catalysts, it seems, don't distinguish between good and bad. They only follow chemistry's rules. You might think of photosynthesis as light magic, but it's catalysis too. Chlorophyll absorbs photons and transfers their energy to water and carbon dioxide molecules, creating glucose. The process depends on manganese clusters that break apart water molecules, nature's invisible electrolysis machine. Every tree, every blade of grass is covered in microscopic catalysts, tirelessly turning sunlight into matter. Without them, the world would be dark and hungry. Catalysis even shapes outer space. In the freezing darkness between stars, dust grains coated with ices of water, ammonia and carbon monoxide host tiny reactions that build complex organic molecules, formaldehyde, methanol, even amino acids. The solid surfaces act as cosmic catalysts, letting atoms meet and bond that otherwise never would in the vacuum. Historians still debate whether life's first chemistry began in such places, invisible laboratories adrift in starlight long before Earth was born. Invisible catalysts also rule your emotions, though you might not realize it. Neurotransmitters don't just appear. Enzymes catalyze their creation and breakdown. The feeling of calm after stress? That's monoamine oxidase quietly dismantling excess adrenaline. The focus you gain after caffeine? That's because caffeine blocks adenosine receptors, catalytically prolonging alertness. The line between chemistry and consciousness grows thinner with every invisible reaction. Industrial chemists have taken the hint, designing synthetic catalysts that mimic enzymes. They build molecular cages, metal clusters, and organic frameworks that fold, twist, and beckon like proteins. These artificial catalysts make fertilizers, plastics, and medicines at scales nature never dreamed of. The Haber-Bosch process, for example, uses an iron catalyst to fuse nitrogen from the air with hydrogen into ammonia, fertilizer that feeds half the planet. That one invention turned invisible atmospheric chemistry into bread on the table. Of course, catalysts don't always behave. Some poison themselves, binding too tightly to byproducts or impurities. Others demand precise conditions, the wrong pH, the wrong heat, and they sulk into inactivity. Keeping them happy requires finesse. The same goes for biological catalysts. Enzymes denature when overheated, losing their delicate folds. That's why high fever is dangerous. The invisible catalysts of life start misfiring. Historians still argue whether catalysis is chemistry's greatest principle or simply its most pervasive. It's certainly the most democratic. From galaxies to mitochondria, from ocean vents to kitchen ovens, catalysts make change possible. They're the unsung translators between potential and reality, energy and form, intention and result. You take a deep breath and think about how much of your existence depends on unseen mediators. How the enzymes in your stomach, the chlorophyll in leaves, the metals in machines, all share the same purpose: to help matter become something else. Catalysts remind you that transformation is natural, that nothing truly happens alone. The invisible hand that moves chemistry forward moves you too, quietly, efficiently, and always just in time. You glance toward the window and for a heartbeat towards, it looks as if there's nothing between you and the outside world. Yet the glass that separates you from the air is itself a chemical paradox. A solid that behaves like an invisible liquid. A barrier that lets light pass as if it weren't there at all. The chemistry of transparency is one of nature's subtler illusions, how matter decides when to reveal itself and when to hide. Tonight, we wander through that clear curtain, exploring why some things vanish in plain sight, how glass cheats structure, and what it means for something to be truly invisible. Glass is not, as many believe, a frozen liquid. It's an amorphous solid, a tangle of silicon and oxygen atoms arranged without the tidy repetition of a crystal. When molten silica cools quickly enough, its atoms lock into place before they can align, forming a random network that light passes through almost unhindered. The irregularity, ironically, creates clarity. Each bond bends and twists at chaotic angles, but because the structure is uniform on the scale of light waves, photons slip through as though nothing were there. What you're really seeing when you look through glass is space sculpted by chemistry. Historians still argue whether glass-making began by accident or intention. One favourite story tells of ancient Phoenician traders who set their cooking pots on the blocks of natron near a sandy shore. The fire melted the sand and soda together, forming a glossy puddle. Whether that tale is truth or legend, archaeological evidence shows that glass beads appeared in Mesopotamia more than 4,000 years ago, long before anyone knew what silicon was. Those first artisans were performing molecular engineering by instinct, melting sand, ash, and limestone into a substance that captured sunlight and held it captive. A quirky tidbit: medieval stained glass artists often noticed that old church windows were thicker at the bottom than the top, and assumed the glass had slowly flowed downward over centuries. Modern chemistry spoiled the romance. Glass at room temperature doesn't flow at all. It's just uneven from old manufacturing methods. The The illusion of movement belongs to time, not to matter. Still, it's fitting that the material of transparency invites myths about motion. When light enters glass, it slows down, bending as it crosses the boundary between air and solid. That refraction makes lenses possible, simple curved pieces of invisible matter that have rewritten human destiny. Through glass, Galileo saw moons orbiting Jupiter. Through glass, Van Leeuwenhoek discovered bacteria. The microscope and the telescope, both born from the chemistry of silica, stretched perception from the cosmic to the microscopic. Invisible worlds became visible, all because glass quietly refused to block light. Yet glass is selective. It lets visible light through, but absorbs most ultraviolet and infrared radiation. That's why sunlight warms a greenhouse. Visible light enters, but the re-emitted infrared from inside can't escape. This greenhouse effect on a planetary scale keeps Earth habitable, proof that even transparency has consequences. The same chemistry that grants glass its clarity also helps trap heat in the sky. Invisible doesn't mean innocent. Look closer, literally, and you'll find that transparency depends on how light interacts with electrons. In metals, free electrons reflect photons, giving shine, but no visibility. In opaque stones, electrons absorb certain wavelengths, turning energy into colour. But in glass, electrons sit too tightly bound to jump under visible light's energy. The photons pass through because there's nothing available for them to excite. Transparency is, at its heart, a failure to absorb, a silence where other materials shout. There's a humbler version of transparency too, the chemistry of water. Liquid water, though seemingly colourless, is faintly blue because it absorbs red wavelengths ever so slightly. Pour it deep enough, say an ocean, and the tint becomes visible. Water, glass, and even the air between them owe their near invisibility to the same principle. Molecular bonds that politely ignore most of the visible spectrum. You see right through them, not because they aren't there, but because they refuse to answer when light knocks. Historians still debate whether ancient alchemists viewed glass as a metaphor for purity or transformation. In Egyptian temples, priests wore transparent quartz amulets to symbolize clarity of spirit. In medieval Europe, glassblowers were sometimes accused of witchcraft. To turn dirt into something invisible seems suspiciously divine. It's easy to see why. The process is alchemy in the truest sense, taking chaos and heat and yielding order you can't see. Modern glass is a far cry from sand and ash. Chemists now tailor its properties with boron, lead, or rare earth elements to create glasses that bend light precisely for fibre optics or block radiation in spacecraft windows. Some formulations can even self-heal or darken when exposed to ultraviolet light. Those invisible tweaks in composition turn something ancient into something futuristic. When you hold a smartphone, you're touching transparent armour, toughened through chemical ion exchange that replaces smaller sodium ions with larger potassium ones. You swipe your finger across centuries of chemistry every time you check the weather. Transparency also lives in living tissue. The cornea of your eye, made of collagen, is transparent not because its molecules are different, but because they're arranged so uniformly that light scatters minimally. The same goes for jellyfish bells and some deep-sea creatures whose invisibility depends on proteins spaced just right. Evolution too is a glassmaker, crafting bodies that vanish into their surroundings, invisible chemistry perfected by survival. A quirky modern twist, scientists have created invisibility cloaks using metamaterials, engineered substances that bend light around objects. They work not by erasing matter, but by guiding photons in precise arcs, leaving the observer none the wiser. The dream of true invisibility, once fantasy, now flickers at the edge of physics. And yet, it's all chemistry in disguise, control of atoms, electrons, and light's invisible choreography. When you glance again through your window, you might notice faint reflections ghosting over the glass, the reminder that transparency is never total. A few photons always bounce back, carrying your face's image into the dark. Perfect invisibility, it turns out, doesn't exist. Even the clearest pane holds a whisper of itself, a shimmer of resistance against the idea of pure emptiness. And maybe that's the secret charm of transparent things. They let you look beyond them, but never entirely forget they're there. Glass, water, air, they're nature's quiet mediators, turning the invisible visible and back again. You're surrounded by them every waking moment, enclosed by their chemistry, guided by their light. So when you next reach out and press your hand to a window, feel the subtle coolness beneath your fingertips and remember, You're touching matter's most delicate trick, solidity that hides in plain sight, invisibility built from perfect imperfection. You take a slow breath and imagine shrinking smaller and smaller past cells, past molecules, until even atoms loom like planets. The world dissolves into haze, edges blur, and matter itself stops behaving politely. Welcome to the quantum shadows, where invisibility becomes the rule rather than the exception. Down here, chemistry is less a set of tidy equations and more a swirling probability storm. You can't point to where an electron is, only where it might be. Every atom you've ever touched, every breath you've ever taken, is built from these invisible ghosts pretending to be solid. Each atom you encounter, whether in your skin or the stars, is mostly empty space. The nucleus, the dense core of protons and neutrons, is a speck compared to the orbiting cloud of electrons. If an atom were the size of a football stadium, the nucleus would be a marble at the centre, and the electrons would be faint mist near the bleachers. The rest? Pure emptiness, structured by invisible forces. And yet, from that emptiness, everything tangible arises. It's chemistry's most poetic contradiction, solidity made from vacancy. Historians still argue whether the modern image of the atom owes more to Niels Bohr's mathematical neatness or to Schrödinger's uneasy imagination. Bohr saw electrons as little planets circling a sun-like nucleus, a model simple enough for school posters, but ultimately wrong. Schrödinger replaced those orbits with clouds, probability zones where electrons might be found. He even suggested that until measured, an electron exists everywhere at once. Invisibility here isn't a property, it's a principle. Observation itself becomes a kind of chemistry, collapsing potential into reality. A quirky tidbit. In 1927, Werner Heisenberg proposed his uncertainty principle, the idea that you can know an electron's position or momentum, but never both precisely. The better you pin down where it is, the less you know how fast it's moving. The invisible, it seems, demands privacy. Heisenberg's insight rattled scientists who longed for certainty. Einstein famously grumbled, "God does not play dice with the universe," to which physicist Niels Bohr might as well have replied, "Stop telling God what to do." The strange part is that these invisible rules manifest in visible chemistry all the time. The colours of metals, the bonds in molecules, the way atoms share or steal electrons, each depends on quantum behaviour. Copper gleams red-orange because its electrons absorb and emit light at just the right energies, a property born from invisible electron transitions. Water's shape, its bent angle, its polarity, comes from quantum repulsion between orbitals. You drink quantum mechanics every morning without realising it. If you could hover near a hydrogen atom, you wouldn't see a miniature solar system. You'd see a blurry cloud, densest near the nucleus, fading outward, a 3D probability fog. The electron isn't whirling, it's smearing. Its behaviour is described not by paths but by wave functions, mathematical ghosts that predict outcomes, not certainties. Chemistry builds its castles atop these equations, trusting patterns no eye can ever witness. Invisible mathematics yields visible matter, a trick so audacious it almost feels mystical. In this quantum mist, even bonding becomes a negotiation between invisibilities. When two hydrogen atoms meet, their electron clouds overlap, forming a region of shared probability, where attraction to both nuclei balances repulsion. That overlap, the invisible handshake of wave functions, is a covalent bond. Break it, and the energy released can power stars or cells. Invisible math becomes tangible fire. Somewhere between order and chaos, particles also flirt with duality. Electrons act like both waves and particles depending on how you look. Shine light through two tiny slits, and electrons create an interference pattern, like ripples overlapping in a pond. Watch them too closely and the pattern collapses, each electron choosing a single slit as if embarrassed. Historians still debate whether observation changes reality or merely reveals one version of it. The universe seems to insist that knowing and seeing are the same act. Quantum chemistry goes further, suggesting that invisibility can be borrowed or shared. In phenomena like tunnelling, particles slip through barriers they shouldn't be able to cross, as if winking between possible worlds. Your body relies on this absurdity in the enzymes that let hydrogen atoms tunnel during reactions, making metabolism possible. Without quantum tunnelling, digestion would stall, stars couldn't fuse hydrogen, and chemistry itself might freeze. The invisible cheat code of the universe, hidden in plain math. A quirky modern echo of that invisibility, the electron microscope. It doesn't see in light at all, but in waves of electrons, exploiting their tiny wavelengths to reveal atoms. When scientists first resolved atomic lattices, they stared into what had always been invisible and found geometry. Yet even then, what they saw wasn't electrons themselves, but the echoes of their probability patterns. You can photograph invisibility only by watching how it disturbs something else. Even temperature owes its existence to the quantum world. Heat is just the average motion of particles, each vibrating according to invisible energy levels defined by quantum laws. Absolute zero, minus 273.15 degJs, is the point where motion theoretically stops, yet quantum uncertainty ensures that atoms still quiver faintly. They can't be perfectly still. Invisibility forbids perfection. That ghostly residual motion called zero-point energy means the universe can never truly rest. Historians still argue whether quantum mechanics explains consciousness, whether the brain's microtubules or synapses exploit quantum coherence. The idea divides scientists into believers and skeptics, half calling it elegant speculation, half calling it pseudoscience. Maybe thought itself is the universe briefly observing its own invisibility, maybe not. Either way, the notion is irresistibly poetic, that somewhere beneath awareness, your neurons hum with probabilities, collapsing and recombining as ideas. When you return to normal scale, when atoms shrink back to invisibility and your world regains its edges, you carry a strange comfort. The solidity of the chair beneath you, the warmth in your hands, even the words you're hearing now, are the end result of quantum indecision settling into order. The invisible chaos beneath matter doesn't threaten reality, it sustains it. The uncertainty that governs electrons also gives rise to stability, form, and life. So as you drift toward rest, remember that the space around you and within you isn't empty at all. It's humming with invisible waves, particles, and probabilities all conspiring to appear calm. You're made of quantum fog briefly holding its breath, a collection of shadows pretending to be solid. The chemistry of the invisible doesn't end at sight. It begins at the point where sight fails. Down there, in the hush between atom and void, everything glows with possibility, seen only by imagination. You rest your palms on your knees, feeling the faint sheen of warmth from your skin, and you can almost sense the invisible chemistry of emotion humming underneath. Fear, excitement, anxiety. They all feel psychological, but in truth they are biochemical storms, molecular signatures written in sweat and breath. Tonight we're following the trail of scentless fear, the invisible signals that bodies give off when stress rewires chemistry. You might not smell it, but your cells certainly do. The moment fear flickers across your awareness, your amygdala, the brain's little almond of panic, fires without asking permission. In milliseconds it sends messages to your adrenal glands perched atop your kidneys, ordering them to release adrenaline and noradrenaline. These molecules surge into the bloodstream, invisible messengers that accelerate heartbeat, tighten muscles, and sharpen senses. Is the body's ancient chemistry, unchanged since the first creature decided that run was a better option than think. Historians still argue whether fear's chemistry evolved purely for survival or also for communication. After all, other animals don't just feel fear, they broadcast it. A mouse that catches a whiff of its predator's scent releases alarm pheromones that send nearby mice darting for cover. Deer emit volatile compounds through skin glands when startled, and insects are masters of chemical panic. Ants, for example, release formic acid when crushed, warning the colony of danger. The chemistry of fear is social long before it becomes emotional. Humans too may share that ancient broadcast, though far more subtly. In controlled experiments, volunteers exposed to the sweat of anxious skydivers showed heightened activity in brain regions tied to vigilance. The sweat itself had no noticeable odour, yet its molecules carried invisible messages. Researchers suspect that steroid-like compounds, androstenone, cortisol derivatives, and perhaps other unidentified molecules act as unconscious cues. You smell fear not as a scent, but as a shift in your nervous system. You don't notice, your chemistry does. A quirky tidbit. The term cold sweat isn't poetic exaggeration. Adrenaline doesn't just raise heartbeat, it also activates sweat glands even in cool conditions, prepping your skin for thermoregulation during a potential sprint. Each droplet of moisture is a mix of water, salts, and trace organics that evaporate to cool the body. In fear, that reaction is overclocked. You sweat more, breathe faster, and lose fine motor control. Your invisible chemistry chooses speed over precision. Inside, cortisol takes the longer view. Released moments after adrenaline, it keeps your body primed, mobilizing glucose, suppressing digestion, sharpening memory. For hours afterward, you remain on biochemical alert. That invisible persistence explains why stress lingers long after the danger has passed. Your chemistry hasn't gotten the memo that the tiger is gone. It's still bracing for round 2. Over time, this invisible vigilance becomes toxic, damaging tissue and dampening immunity. Chronic stress, in chemical terms, is fear without expiration. Historians still debate whether the word fear itself once described emotion or omen. In ancient texts, fear was often externalized, something sent upon people by gods, not generated within. Only with modern anatomy did we locate it inside flesh, where invisible molecules replaced invisible deities. Yet the ritual remains. Fear arrives uninvited, invisible, and potent. The difference is that now we can name its molecules. The chemistry of fear doesn't stop at hormones. It changes the body's scent profile, not just in sweat, but in breath. When you're frightened, your metabolism shifts toward anaerobic respiration, increasing lactic acid production. Some of that acid escapes through skin and exhalation, altering your odor in ways animals can detect. Dogs trained to sense anxiety respond to those invisible cues with uncanny precision. They smell the chemistry of thought. But there's another invisible side to fear, its paradoxical usefulness. The same hormones that make your hands tremble also sharpen reaction times and memory consolidation. After a fright, your brain records sensory details with heightened clarity, a mechanism meant to improve future survival. It's why you can recall near misses in vivid detail decades later. Fear leaves a biochemical watermark on memory, a scentless chemical note reminding your neurons, don't forget this. There's also the quiet aftermath, the counter-chemistry of calm. Once the perceived danger fades, the parasympathetic nervous system takes over, releasing acetylcholine to slow heartbeat and relax muscles. Endorphins, the body's natural opioids, soften pain and bring a subtle high, the relief rush. Serotonin and oxytocin follow, restoring trust and safety. The invisible dialogue between stress and peace begins anew. You might sigh, not realizing that your breath is the audible signature of chemical equilibrium returning. A curious study once found that laughter can lower cortisol levels within minutes. The chemistry of joy, it seems, directly dissolves the chemistry of fear. That's why gallows humor works, why soldiers joke in trenches or surgeons crack dry remarks mid-operation. Invisible molecules are the real audience for those jokes. They laugh first, easing the body's vigilance. Even your immune system eavesdrops on fear. Adrenaline and cortisol can temporarily suppress inflammation, but chronic exposure does the opposite, leaving you more vulnerable to illness. Invisible messengers connect emotions to immunity, proving that what you feel has chemical consequences. Ancient healers spoke of spirit and humor. Modern science just calls it endocrine crosstalk. Different vocabulary, same invisible truth. And yet fear's chemistry can also unite. Think of a crowd gasping together at a sudden noise, their pulses synchronizing, their pupils dilating in unison. Invisible signals, hormones, pheromones, subtle changes in breathing, ripple through the group, aligning biochemistry like an unseen current. Shared fear becomes cohesion, the primal glue of tribes and teams. You could call it social catalysis, an ancient defense mechanism now repurposed for movie nights. When you calm again, your chemistry rebalances, but traces remain. Adrenaline degrades into metabolites excreted in urine. Cortisol levels ebb slowly. You're a biochemical tide, forever rising and falling with invisible emotion. What you call courage is not the absence of fear. It's the ability to let these invisible waves crash through you and then recede. So as you sit there now, heartbeat steadying, breath deep and even, remember that the invisible chemistry of fear isn't your enemy. It's proof of life's alertness, the ancient molecular code that keeps you awake to the world. You don't need to see it or smell it to respect it. Fear is the quiet pulse beneath courage, a scentless reminder that being alive means reacting to threat, to safety, to the endless, invisible symphony within your blood. You rub your thumb along your wrist, feeling the faint beat beneath the skin, and think about how fragile that rhythm really is, how easily invisible molecules can tilt it off balance. The chemistry of toxins and antidotes hides in plain sight, a game of mimicry and timing played at the molecular level. The most dangerous substances are rarely the ones you can see, taste, or smell. They're ghosts, colourless gases, clear liquids, powders that vanish into water. Yet within their invisibility lies power enough to still a heart or blur a thought or save a life. Every toxin begins as chemistry slightly out of place. A molecule shaped just similar enough to trick the body but just wrong enough to break it. Take carbon monoxide, for instance, the silent thief of oxygen. It slips into your lungs unnoticed, binds to hemoglobin 200 times more tightly than oxygen, and refuses to let go. Your blood turns bright cherry red, a cruel mockery of vitality even as your cells suffocate. No smell, no irritation, just the invisible swap of life for imposter. It's the perfect assassin precisely because it's chemistry doing what chemistry always does, seeking the strongest bond. Historians still argue whether Emperor Napoleon met his end through deliberate poisoning or slow exposure to arsenic-laced wallpaper. The pigments of the 19th century, brilliant greens made from copper arsenite, released toxic vapours in damp rooms. The invisible turned decorative, then deadly. Victorians, forever trusting appearances, filled their homes with slow-acting chemistry disguised as fashion. Invisible death has a way of dressing itself in elegance. The body's defences against toxins are themselves chemistry in motion. The liver, that unsung biochemical refinery, is packed with enzymes, cytochrome P450s, that modify foreign molecules, attaching hydroxyl groups or cleaving bonds so they become water-soluble and can be excreted. It's invisible detox, constant and automatic. Yet sometimes the process backfires. Certain compounds become more dangerous after metabolism, a cruel irony where the antidote and the poison share the same enzyme. A quirky tidbit, the toxin in pufferfish, tetrodotoxin, is so potent that a dose the size of a pinhead can paralyze the diaphragm, stopping breath without stopping consciousness. The molecule works by blocking sodium channels in nerves, silencing the electrical chatter that allows muscles to move, and yet, handled properly, it's been studied as a potential anesthetic. The difference between medicine and poison, Paracelsus said in the 16th century, is only the dose. The invisible chemistry of life depends on that razor's edge. Alcohol, the world's most socially accepted toxin, operates invisibly too. Ethanol molecules slip across cell membranes, interfering with neurotransmitters like GABA and glutamate. They dampen signals, slow reflexes, soften inhibition. Then enzymes in your liver, alcohol dehydrogenase and aldehyde dehydrogenase, race to dismantle the damage, converting ethanol to acetaldehyde and then to harmless acetic acid. That middle product, acetaldehyde, is what makes you feel poisoned the next morning. The hangover isn't divine punishment, it's chemistry settling accounts. For every toxin, nature designs an antidote. Snake venom, for instance, is a cocktail of proteins evolved to paralyze or dissolve tissues, but the same structure that makes it lethal also makes it targetable. Antivenoms are made by injecting trace amounts into animals, often horses, then harvesting the antibodies their immune systems create. Each antibody fits the venom molecule like a puzzle piece, neutralizing it before it can act. It's a beautiful irony, one invisible molecule outwitted by another. Historians still debate the origins of the word antidote. In Greek, antidoton means given against. The idea that one poison could counter another fascinated ancient alchemists, who hunted endlessly for universal cures, panaceas that might balance all chemical harm. Mithridates VI, a paranoid king of Pontus, famously dosed himself daily with tiny amounts of toxins, training his body to resist assassination. His invisible chemical armor became legend, though modern toxicology doubts the method's real success. Still, the notion lingers in vaccines, which work on the same principle: controlled exposure forging invisible resilience. Some of the deadliest poisons are invisible by necessity. Nerve agents like sarin and VX disrupt acetylcholine breakdown, flooding synapses with unending signals. Muscles lock, lungs seize, consciousness fades, all because a molecule a few atoms wide jams one enzyme. Yet that same chemistry inspired modern medicines. The first Alzheimer's drugs, for example, use controlled enzyme inhibition to prolong neurotransmitter life, easing memory loss. Once again, chemistry plays both villain and saviour in the same act. Invisible antidotes are equally miraculous. Activated charcoal, a fine black powder with immense surface area, can bind toxins before they're absorbed. It doesn't react, it simply traps molecules through van der Waals forces, tiny electromagnetic whispers between atoms. In hospitals, it's administered for overdoses, a black dust swallowing invisible poisons. You can't see the binding, but you can watch life return as the chemistry silences itself. Sometimes the antidote is time itself. Many toxins degrade or are flushed from the body naturally, leaving enzymes to rebuild normal balance. Others require deliberate counteraction: naloxone for opioids, atropine for nerve agents, oxygen for carbon monoxide. Each works by stealing the binding site or outcompeting the toxin, a molecular tug-of-war invisible to the naked eye but decisive in outcome. In the environment, invisible toxins play a slower game. Heavy metals like mercury and lead mimic vital ions, sneaking into enzymes where they don't belong. Mercury binds sulfur in proteins, bending their shape until function collapses. Lead replaces calcium in bones, a ghost element hiding in plain sight. Whole generations have been marked by such invisible chemistry, from Roman lead pipes to 20th century gasoline additives. The poison of progress is often colourless, and yet, invisibility also protects. Antioxidants, invisible defenders in fruits and cells alike, scavenge reactive oxygen species before they can damage DNA. Vitamin C, glutathione, and countless other molecules perform quiet heroics, neutralizing radicals that would otherwise age and unravel tissue. They are antidotes born of evolution, proof that nature knows how to outwit its own chaos. You glance down at your hands, at the faint pulse threading through veins, and realize how narrow the line truly is. The same invisible chemistry that can kill can also cure. It's all about shape, charge, timing, who binds first, who lets go last. Every medicine you've ever swallowed, every breath you've ever taken, is an invisible negotiation between harm and healing. The next time you hear the word toxic, remember that it's not evil, it's energy misplaced. Molecules don't care whether they save or destroy, they only react, obeying rules older than life itself. The invisible chemistry of toxins and antidotes is the purest reflection of nature's neutrality, a silent, elegant balance between danger and deliverance. And in that balance, life endures, fragile, fearless, and forever chemical. You open the window a crack and feel the faint difference in the air, a whisper of warmth that doesn't belong to the season. It's not your imagination. The chemistry of the atmosphere is changing molecule by molecule in ways you can't see but can already feel. This is the invisible hand of climate, a silent sculptor that works not in decades but in atoms, rearranging gases, trapping heat, rewriting weather. You can't smell carbon dioxide or methane, yet they're the architects of the world you're stepping into. Tonight, we drift through the unseen chemistry that governs the fate of the planet. The air you breathe contains just over 0.04% carbon dioxide, a fraction so small it sounds trivial, yet that fraction determines global temperature. Each molecule acts like a microscopic blanket, absorbing infrared radiation from Earth's surface and releasing it in all directions. The physics is simple enough. Light from the sun passes through easily, warms the ground, and the Earth radiates heat upward. Greenhouse gases intercept that heat, trapping it within the lower atmosphere. Invisible, colourless, odourless, but powerful enough to shift oceans and carve new coastlines. Historians still argue whether the first warning came from the chemist Svante Arrhenius in 1896, or from the Irish physicist John Tyndall 30 years earlier. Tyndall demonstrated that water vapour and carbon dioxide absorb infrared radiation while oxygen and nitrogen do not, essentially discovering the greenhouse effect in a London basement using gas tubes and candlelight. Arrhenius, decades later, calculated that doubling CO2 could raise global temperature by several degrees. At the time, he thought it might be beneficial. A warmer Sweden sounded appealing. Invisible chemistry always takes its time revealing consequences. Carbon dioxide is the celebrity of climate change, but methane is its more mischievous understudy. Molecule for molecule, methane traps about 80 times more heat than CO2 over 20 years. It leaks from rice paddies, landfills, oil wells, and even the stomachs of cows whose digestive bacteria belch invisible plumes of hydrocarbon into the sky. You can't see a single puff, yet satellites now map these emissions from orbit, ghostly signatures curling above pastures and pipelines. The chemistry behind this warming is elegant and ruthless. Infrared light carries energy in specific wavelengths, and greenhouse gases vibrate in resonance with those wavelengths. Their bonds stretch, bend, and twist as they absorb the energy, converting it into molecular motion, heat. Oxygen and nitrogen, symmetrical and simple, ignore infrared entirely. Carbon dioxide, with its uneven geometry, dances with it. Methane twirls even more energetically. Nitrous oxide and ozone add their own steps. The atmosphere, it turns out, is a molecular ballroom that never stops moving. A quirky tidbit. In the 1950s, Charles Keeling began measuring atmospheric CO2 at Mauna Loa Observatory in Hawaii, using infrared absorption spectroscopy. His results, now known as the Keeling curve, showed a steady annual rhythm, CO2 rising in winter as plants slept, falling in summer as they bloomed, yet creeping higher overall each year. That invisible climb from 315 parts per million to over 420 today is the heartbeat of the modern climate. You can't hear it, but every storm, drought, and shifting season taps along to its rhythm. Invisible chemistry extends beyond temperature. When CO2 dissolves in seawater, it forms carbonic acid, subtly lowering the ocean's pH. That small shift, from 8.2 to about 8.1, may seem harmless, but it changes how calcium carbonate forms, making it harder for corals and shellfish to build their skeletons. The ocean, Earth's greatest carbon sink, is quietly turning sour. Divers in some regions now hear the brittle crunch of dying reefs, the sound of invisible acid etching through life's architecture. Historians still debate whether humanity's relationship with carbon began with fire or farming. Some argue that burning forest for agriculture thousands of years ago already nudged climate subtly warmer. Others mark the 18th century steam engine as the true starting gun. Either way, the story is chemical. Humans found ways to free ancient sunlight stored in carbon bonds, coal, oil, gas, and in doing so rewrote the composition of the sky. Each flick of a lighter or turn of an ignition key is a continuation of that invisible revolution. But not all is despair. The same chemistry that traps heat can also be turned toward balance. Plants remain the most graceful chemists of all. Through photosynthesis, they draw CO2 from the air, using sunlight to split water and fix carbon into sugars. Each leaf is a microscopic laboratory conducting the reverse of combustion, a quiet antidote to centuries of fire. Modern researchers are mimicking that trick, designing artificial leaves, catalysts that use sunlight to turn carbon dioxide back into fuel or solid carbon. The invisible can be reversed by equally invisible ingenuity. Another ally hides in the soil. Microbes in wetlands, tundra, and farmlands constantly mediate the flow of greenhouse gases. Some consume methane, others release it. A shift in temperature or moisture tilts the balance. Climate, therefore, isn't just air, it's chemistry in dirt, ice, and root. Invisible reactions beneath your feet determine the colour of sunsets decades from now. The upper atmosphere plays its part too. As CO2 increases, it cools the stratosphere, altering jet streams and expanding tropical zones. Weather patterns, once predictable, begin to meander. Droughts deepen, storms intensify, oceans climb. None of these changes has a single hue or odour, through invisible consequences of invisible molecules. The most transformative forces of the century are, quite literally, transparent. And yet, invisibility cuts both ways. Renewable energy, carbon capture, and reforestation all hinge on unseen chemical innovations. Hydrogen fuel cells produce only water vapour. Perovskite solar panels harvest light with atomic precision. Even the electric battery in your hand relies on lithium ions shuttling invisibly between electrodes. The future's chemistry will be as intangible as the air itself, quiet, clean, unseen. Still, the atmosphere keeps its ledger. Every molecule of CO2 lingers for centuries. Every methane puff fades but leaves a mark. The balance sheet of invisible chemistry is patient but strict. You can't bargain with physics, only adapt your chemistry to match its truth. As you gaze at the horizon, maybe you'll notice how the air shimmers a little differently these days. Thicker, warmer, carrying the weight of human breath multiplied by billions. The invisible hand of climate is not a distant threat. It's already on your cheek, in your lungs, in the shifting rhythm of seasons. The molecules we release return as weather, as ocean tides, as the faint change in wind through your window tonight. The chemistry of the invisible never forgets, but perhaps it forgives if we learn to listen before the silence turns to storm. You close your eyes for a moment and imagine rising, higher than clouds, past the blue of the stratosphere, through the thin scatter of the thermosphere, until the air finally gives up and the stars no longer twinkle. Out here, chemistry seems impossible. The word vacuum feels final, as if emptiness has won. But the universe, even at its quietest, is never truly silent. Between the stars drifts the faintest breath of matter, molecules so sparse they might wait years before meeting another of their kind. This is the chemistry of the void, an invisible network connecting galaxies, shaping worlds, and writing the story of everything that has ever been. A cubic centimetre of interstellar space contains, on average, just one atom, maybe two if the neighbourhood is busy. Yet scattered across light years, those atoms organise themselves into vast clouds of gas and dust. Hydrogen dominates, its simplest molecule H2 forming in the cold shadows where starlight can't tear it apart. Carbon, oxygen and nitrogen join in, assembling water, ammonia, methanol, formaldehyde, molecules that shouldn't exist but do, clinging to dust grains made of silicates and ice. Invisible reactions take place on these frigid surfaces, one atom landing, another following until bonds form. The void, it turns out, is a chemist's workshop that just prefers long deadlines. Historians still argue whether cosmic chemistry began before or after the first stars. Some theories suggest that molecules like hydrogen and helium hydride, the universe's first compound, formed just a few 100,000 years after the Big Bang, when temperatures cooled enough for electrons to settle. Others believe that heavier elements forged in the first supernovae had to shatter before real chemistry could begin. Either way, the universe's invisible reactions predate life by billions of years. Chemistry is older than biology. Molecules are the ancestors of everything. A quirky tidbit: in Kirsten, scientists studying a meteorite that fell in Australia discovered over 80 organic molecules, including amino acids, the building blocks of proteins. These compounds had formed in space, condensed onto dust, and travelled unbothered for eons before crashing into Earth. The same cosmic delivery service has likely visited countless worlds. You are, quite literally, made of interstellar leftovers. When you touch your skin, you're touching recycled stardust refined through invisible chemistry older than oceans. In the coldest reaches of molecular clouds, temperatures drop to a few degrees above absolute zero. Yet even there, reactions continue, driven by cosmic rays and ultraviolet light sneaking through dust. These rays ionize atoms, setting off cascades of electron exchanges that birth new molecules. Astronomers detect them not by sight but by radio waves, specific frequencies emitted as molecules rotate and vibrate. Each invisible molecule sings its own signature note. By listening to those faint songs, telescopes have identified more than 200 distinct compounds adrift dreamers between stars. The cosmos hums in chemistry's key. Closer to home, the solar system carries its own invisible laboratory. Comets, dirty stobles of the ice and rock, preserve the molecular recipes of the early solar nebula. When sunlight warms them, jets of gas erupt, releasing water, carbon dioxide, methane, and complex organics into space. Every comet tail is a temporary atmosphere, a glowing fingerprint of chemistry frozen for billions of years. Historians still debate whether Earth's oceans arrived this way, carried by ancient impacts that rained invisible molecules until water pooled and stayed. Even emptiness has structure. The interstellar medium weaves filaments of gas across galaxies, shaped by magnetic fields and supernova shockwaves. Within these filaments, denser knots collapse under gravity to form new stars, and around those stars, disks of gas and dust spin into planets. It's an invisible cycle. Stars forge elements, scatter them in death, and rebuild new worlds. Every carbon atom in your breath, every calcium atom in your bones was smelted in a star's heart, then ejected into space to cool, combine, and someday breathe again. The universe recycles at a scale too vast to imagine, one molecule at a time. The chemistry of the void isn't limited to birth, it also dictates death. When stars burn through their hydrogen fuel, helium and heavier elements fuse in their cores, creating layers like an onion. Eventually, balance fails and the star collapses, triggering explosions that scatter enriched material across space. Those shockwaves drive new reactions, smashing atoms together in moments of violent intimacy. The invisible hand of physics writes chemistry's next chapter in light years and millennia. A quirky cosmic twist. In the Orion Nebula, astronomers have found simple sugars, glycolaldehyde, floating freely in space. Another region, Sagittarius B2, hosts ethyl formator, the molecule that gives raspberries their scent. The centre of our galaxy literally smells faintly of fruit and rum. It's an absurd and wonderful reminder that chemistry doesn't stop at Earth's edge. It permeates the cosmos, building flavour, colour and possibility where no eyes or tongues exist to sense them. Invisible chemistry also sculpts planets long after they form. On Titan, Saturn's largest moon, methane rains from orange clouds into liquid lakes. Sunlight filtered through nitrogen haze drives reactions that form complex hydrocarbons, precursors to life. On Mars, ultraviolet light splits carbon dioxide, hinting at ongoing reactions that may once have supported a denser, wetter atmosphere. Even the icy moons of Jupiter hide invisible oceans of salty water beneath crusts of ice, where heat from tidal forces could fuel chemical energy like Earth's deep-sea vents. The cosmos is not dead, it's quietly simmering. Historians still argue whether life itself began in such cosmic chemistry. Did amino acids delivered by comets mix with Earth's early oceans to form proteins? Or did lightning in volcanic skies spark life locally? Every experiment edges closer, yet the answer remains elusive, an invisible truth waiting beneath layers of time. What's certain is that space is not sterile. Every nebula and comet carries hints of the same molecules that pulse in your veins. Even now, satellites orbit Earth, sniffing the thin air of the exosphere where atoms escape into space. Instruments detect traces of hydrogen, helium, and even oxygen drifting away. Earth breathes into the void, and the void responds with starlight, cosmic rays, and the occasional meteor returning what was lost. The balance between emptiness and matter, between invisible and visible, never stops adjusting. So when you look up at the night sky and think of it as empty, remember what's truly there. Chemistry in its most patient form. Every photon of starlight you see has passed through invisible oceans of gas, each molecule bending, absorbing, and re-emitting light in its own tempo. You're not looking into nothingness, you are watching chemistry stretch across infinity. The void, far from being lifeless, is the womb of all matter, the laboratory that never closes. Somewhere out there right now, two hydrogen atoms are meeting for the first time, forming a molecule that may, billions of years from now, flow through the bloodstream of a living creature. The universe may look still, but the chemistry of the invisible is always at work, quiet, cold, and endlessly creative. You open your eyes, and the world seems ordinary again, the lamplight soft, the air unmoving. But the truth is that you are surrounded by hidden vision. Everything you see has already been translated from the invisible. For centuries, humanity has tried to peer into what light refuses to show, to catch the molecules mid-dance and the atoms mid-whisper. This is the story of how we learned to see the unseeable, how chemistry itself became visible through ingenuity and stubbornness. It began with light, always light. In the 17th century, Isaac Newton passed a beam of sunlight through a prism and discovered that white was not pure, but a chorus of colours. Each hue, he realised, bent differently, proof that light carried structure. Historians still argue whether Newton's experiment was physics or protochemistry. Either way, it marked the first time invisibility cracked. When scientists later learned that different substances absorbed or emitted distinct colours, a new language was born, spectroscopy, the alphabet of atoms. By the mid-1800s, chemists Gustav Kirchhoff and Robert Bunsen, yes, of burner fame, noticed that heated elements produced unique patterns of light when viewed through a prism, spectral fingerprints that revealed identity. Sodium glowed yellow, copper green, strontium crimson. Invisible atoms spoke through visible fire. Using these spectral lines, Bunsen discovered new elements, cesium and rubidium, without ever seeing them directly. A quirky tidbit. Bunsen's lab notes reportedly described cesium's pale blue flame as the colour of heaven, proof that even in data, poetry survives. Spectroscopy grew more powerful with technology. By the early 20th century, it was sensitive enough to detect elements in distant stars. Astronomers discovered helium in the sun's spectrum decades before finding it on Earth. Imagine that, the chemistry of a star deduced by colour alone. The invisible became readable? Today's telescopes use the same principle, but across every wavelength. Ultraviolet, infrared, X-ray to map galaxies, identify exoplanet atmospheres, and even glimpse molecules forming light years away. You don't just look at starlight anymore, you eavesdrop on cosmic chemistry. Closer to home, new tools made the microscopic world visible. When Antonia van Leeuwenhoek first peered through his handmade lenses in the 1670s, he saw animalcules, tiny beings swimming in a drop of water. He had no idea he was watching bacteria, the architects of invisible life. His microscopes were crude but revolutionary. They revealed that invisibility had been a matter of scale, not absence. Every pond, every mouth, every handful of soil teemed with motion no one had imagined. Then came the electron microscope, a machine that replaced light with streams of electrons, whose wavelengths are 1,000 times shorter. By bouncing them off surfaces, scientists could map atoms themselves. The first atomic resolution images of silicon in the 1950s looked almost unreal. Rows of glowing dots, perfectly ordered. For the first time, we weren't inferring atoms, we were looking at their ghosts made visible through electrons. Historians still debate whether this was chemistry's greatest technological leap or its greatest philosophical one. To see what you'd only believed was there, does that change what belief means? Infrared and ultraviolet imaging expanded sight still further. Infrared cameras translate heat, the invisible vibration of molecules, into visible colour. Ultraviolet photography captures patterns unseen by human eyes, but obvious to insects and birds. Flowers that look uniform to you are streaked with ultraviolet guides pointing toward nectar. In a sense, bees live in a more colourful world because they see chemistry directly. Every wavelength you miss, another species perceives. Your invisibility is someone else's daylight. A quirky detail from modern times. In 1989, IBM scientists arranged 35 xenon atoms on a nickel surface to spell out IBM, using a scanning tunneling microscope. It was both experiment and art, proof that we could not only see atoms but move them one by one. That single image marked the dawn of nanotechnology, a field where invisibility became a canvas for creation. The tiniest letters ever written announced humanity's arrival as co-author of atomic design. Spectrometers today can identify chemicals by how they vibrate, spin, or ionize. Mass spectrometry, for instance, smashes molecules into fragments and measures their masses with such precision that you can deduce structure from the debris. When forensic scientists find a trace of toxin or perfume or ancient pollen, they are reading invisible evidence left by chemistry itself. The air exhaled by a patient can reveal disease through gas chromatography. A single fingerprint can expose diet or stress through metabolites. The invisible has become diagnostic. Historians still argue whether this obsession with visibility changed the philosophy of science. Before these instruments, chemists believed through inference. Reaction, colour, precipitate, afterward, they believed through image. Yet visibility doesn't always mean understanding. Seeing atoms doesn't tell you why they choose partners, why they build beauty or chaos. The risk of visibility is arrogance, the illusion that to see is to know, but chemistry keeps secrets, it always will. Even art owes a debt to invisible seeing. Pigments are chemical structures absorbing and reflecting specific wavelengths. The discovery of synthetic dyes in the 19th century came from William Perkins' failed quest to make quinine. His Mauveine dye accidentally birthed the modern colour industry. Artists who paint with acrylics or photograph with digital sensors are working with molecules designed through spectroscopy, tuned to catch or ignore certain frequencies. Vision itself is a chemical collaboration between eye and material, photons and pigment, visibility and absence. A quirky human twist, medical imaging now lets us see chemistry inside ourselves. MRI scans map hydrogen atoms in water. CT scans track X-ray absorption by calcium and carbon. PT scans follow radioactive tracers through metabolism. Each image is an echo of molecules shifting, decaying or aligning in magnetic fields. When you watch a beating heart on a hospital monitor, you're watching invisible physics translated into visible rhythm. Life, projected in pixels, remains a chemical performance. And so, through centuries of glass, magnet and math, we've peeled back invisibility layer by layer. Yet every revelation only deepens the mystery. The more precisely we see, the more invisible possibilities appear. Quarks beneath protons, dark matter beyond galaxies, quantum fields that ripple through all space. The act of seeing the invisible keeps inventing new invisibilities to chase. You sit quietly and realize that all sight in the end is a form of trust. You trust photons to carry messages, lenses to bend them faithfully, instruments to translate their whispers into something your brain can grasp. What you call visible is just well-interpreted invisibility. The world glows not because light exists, but because your chemistry knows how to listen. So when you gaze at the lamplight tonight, remember how far you've come, from prisms and candle flames to telescopes that read the breath of exoplanets. The invisible world hasn't shrunk, you've simply learned to join it. Light is no longer barrier but bridge, and through that bridge chemistry keeps revealing itself, one photon, one atom, one quiet revelation at a time. You inhale slowly, feeling the air drift down into your lungs, and for a moment you imagine what it would mean to disappear into it, to become invisible not through magic, but through chemistry. The thought isn't as far-fetched as it sounds. Everything you are, every solid atom in your body was once vapor, plasma, or dust. You've already been invisible more times than you can count. So as the night settles around you and the world grows quiet, let's follow that transformation all the way through, how the seen dissolves into the unseen, how you, molecule by molecule, become part of everything else. The first thing you'd notice, if you could notice at all, is warmth. Heat is just molecular motion, and as your temperature rises, the bonds that hold your body together begin to loosen. Proteins uncoil, fats melt, water slips away as vapor. Chemistry doesn't recognize identity, it just follows energy. Soon the molecules that built your breath and heartbeat drift free, joining the air as carbon dioxide, water vapor, ammonia, and countless trace compounds. You dissolve into atmosphere, not vanished but redistributed. The invisible you merges with the invisible world. Historians still argue whether ancient philosophers who dreamed of transmutation, alchemists seeking the philosopher's stone, were chasing metal or meaning. Lead into gold, body into spirit, visible into invisible, the symbols overlap. Modern chemistry achieved what they couldn't, turning matter into energy and back again. But it also revealed that the transformation was never mystical, it was always happening. Atoms move from form to form endlessly, cycling through rock, air, water, flesh. You don't become nothing, you just become elsewhere. A quirky tidbit, the carbon atoms in your body number roughly 10 octillion, and each one will, over centuries, re-enter air, ocean, or soil. Statistically, you will share atoms with every creature that has ever lived. With Cleopatra, with a Tyrannosaurus Rex, with the first tree that found sunlight. Invisibility is not erasure, it's communion. Every breath you exhale contains about 1 billion molecules of oxygen and carbon dioxide that someone else will eventually breathe in. Chemistry, quietly and without ceremony, keeps everyone in circulation. If you shrink the scale further, invisibility becomes fundamental. Atoms themselves don't have color, shape, or texture. What you perceive as solid, your hand, this page, the world, is mostly void, held together by electromagnetic forces. Visibility, in other words, is a cooperative illusion between light and matter. When you disappear, you're simply opting out of that conversation. The photons go on traveling. They just have nothing left to bounce from. In a way, you've already practiced this kind of disappearance. Each time you breathe, countless atoms of water leave as invisible vapor. Every heartbeat propels carbon dioxide outward. Even while sitting perfectly still, you're constantly trading molecules with your surroundings. The border between you and not you is porous, negotiated by chemistry moment by moment. The body isn't a fortress, it's a tide pool in motion, its boundaries blurred by the invisible ebb and flow of air and heat. Historians still debate which discovery truly made humans modern, the splitting of the atom or the realization that atoms themselves recycle endlessly. The first gave us power, the second humility. Invisibility teaches perspective. You can't hold on to molecules, you can only borrow them. The nitrogen in your blood was once part of a lightning bolt. The oxygen you exhale will feed a leaf by morning. You are a temporary constellation of invisible chemistry, self-aware for a blink before returning to the dance. Scientists have begun to explore literal invisibility too, metamaterials that bend light around objects, transparent electrodes, cloaking films that redirect electromagnetic waves. But true invisibility, the kind that matters, isn't about hiding from sight. It's about recognizing connection. When you dissolve into the air, you don't vanish, you blend. In that blending lies the quiet truth of chemistry. Nothing ever truly leaves. It just becomes background, subtle, diffuse, essential, a quirky note from biology. Every breath you take contains a few argon atoms that were once part of Earth's first atmosphere. Argon is chemically inert. It doesn't bond, doesn't burn, doesn't decay. It drifts through eons unchanged, cycling through lungs of dinosaurs, whales, and poets alike. That same invisible gas now threads through you. You're breathing ancient invisibility, inhaling history's chemistry without realizing it. As your awareness drifts, imagine the boundaries softening. Your breath mingles with the air, your body's warmth spreads outward, and what was solid becomes gradient, heat diffusing, molecules dispersing. Invisibility feels less like loss and more like release. The world keeps every part of you, it just scatters the pieces into wider patterns. Somewhere, a molecule once in your blood might soon help a raindrop condense, or feed a blade of grass, or sparkle in a snowflake's lattice. Chemistry is a resurrection disguised as entropy. When you think of it that way, the invisible stops being frightening. It becomes home. You've always lived in it. The unseen air that feeds your lungs, the silent electric pulses that make thought possible, the radiation from distant stars that warms your skin. Visibility is the exception, not the rule. Matter spends most of its existence unlit, unfelt, and unnamed. To live is to briefly shimmer above that sea of invisibility, to be noticed by light for a while before sinking back into the quiet that made you. Historians still argue what it means to be alive in chemical terms. Some say it's organization, others energy flow, still others information. But maybe it's simpler. Life is visibility's brief performance in an invisible theatre. You appear, you act, you fade, and the elements return to the wings to wait for their next role. The show never ends because the actors never die, they just keep changing costumes. So as you sit here breathing, surrounded by air you can't see and reactions you can't feel, remember that invisibility isn't absence, it's continuation. You've been invisible before and you will be again. When that time comes, it won't be an ending. It will be chemistry taking you home, scattering you among stars, rivers, and the pulse of others. You're already halfway there, part of a quiet exchange too intricate to see but too constant to ever stop.